Push to talk 2, 1, 2. Check, 1, 2. Push to talk mic. Okay, that's better. Push to talk mic. 1, 2. Push to talk. And push to talk. So it has to be green for you control that. If you want to let the other board members know that. Thanks. So the laptop audio is quite loud, so when she's testing on the mic, yes. So I'm going to just bring it down. I know that for
yeah, so we'll have to stay on top of the audio levels today because mine it's not like,
Not using it, and I don't think we
no.
have any to present anything, right?
There wouldn't be any presentation from you. But yeah, sure, that's.
Just in
I don't-
case, yeah. Okay.
Sure, 1, 2, okay.
morning and welcome everyone. The workshop today is in respect of BC Hydro's application for a Certificate of Public Convenience and Necessity for the Lower Mainline Reactive Power Reinforcement Project. My name is Anna Fung, and I'm the Deputy Chair of the BC Utilities Commission and the Chair of the panel assigned to hear this matter. With me today are my fellow panel members, Commissioners Andrew Pate Salmon and Anna Denier. And the purpose of the workshop today, as established by Order G823, is to give BC Hydro the opportunity to make a presentation to the BCUC and interveners in order to assist us to better understand the application and allow participants to ask clarifying questions of BC Hydro. The proposed workshop agenda with 4 specific topic areas for discussion was set out in Exhibit A-4, filed by the BCUC on January 16, 2023. I'd like to remind everyone that this workshop is being transcribed and being webcast to the public. Please note that no recordings or rebroadcasts of this workshop will be permitted beyond that maintained by our hearing officers. Transcripts of the workshop will be posted to the BCUC website once they are available. To assist with the transcription, please remember to state your name and whom you represent before speaking, and to spell your last name for the record. If you have any questions during the workshop, please speak up or raise your virtual hand, and someone here will try to maintain the speaker's order. Those in-person participants who have questions should come up to the podium at the front of the room to pose their questions at the microphone so that the court reporters can transcribe the questions for the record. Before we call for appearances, there are a few other housekeeping matters to address. There are several parties participating virtually by Microsoft Teams at this workshop. I would ask that virtual attendees please keep your microphones muted until you're called upon to speak. I may also ask you to turn off your cameras if bandwidth becomes an issue. I'd also like to remind the virtual attendees that if you experience internet connection issues during the workshop, to please phone into the workshop. The call-in instructions should have been provided to you earlier this month. If BC Hydro needs to file any exhibits, it should do so with the Commission Secretary after the workshop in accordance with Part 3 of the BCUC's Rules of Practice and Procedure. I would also like to point out that the BCUC has, after a public comment process, updated the Rules of Practice and Procedure and added Rule 16, which relates to transcripts. Rule 16 outlines the process in the case of a potential transcription error or correction of statements made in the transcript. So please take a note of that. And if you do have any suggestions for corrections to the transcript, please follow Rule 16. And finally, with regards to breaks, we'll try to take breaks at natural points during the day. We'll plan to take mid-morning and mid-afternoon breaks and a lunch break as close to noon as possible, depending on where we are in the agenda. Following BC Hydro's presentation and the question and answer period, I will provide BC Hydro with an opportunity to make any closing remarks should it wish to do so. Now, I'd like to acknowledge and introduce several individuals from the BCUC who play an important role in the review of this application. Niyari Goye is the lead staff for this proceeding, and Avery Jones is the project manager next to her. Lino Busole at the front of the room is our BCUC counsel for this proceeding, and our hearing officer today is E. Decree. Now, as E. Decree is new to our BCUC process and cannot be expected to recognize any of our voices, it's particularly important that all of us identify ourselves and try to speak loudly and clearly into the microphone so that they can accurately transcribe the workshop. We would appreciate everyone's help in that regard. And that's the end of my opening remarks. I will now ask Mr. Busole to call for appearances. Thank you.
Thank you, Madam Chair. Busoli, B-U-S-S-O-L-I, first initial L. First in the order of appearances is British Columbia Hydro and Power Authority.
Good morning, Madam Chair, Commissioners. My name is Sandy Carpenter, just like it sounds. I appear on behalf of BC Hydro. You have our presenters for the workshop in front of you. I won't go through introductions of them. Ms. Nielsen is going to do that, so we don't need to have it on the record twice, I don't believe. Thank you.
Thank you, Mr. Carpenter.
Next is Commercial Energy Consumers Association.
Good morning. My name is Patrick Weaver, counsel to the CEC, the Commercial Energy Consumers Association of BC. I believe with me on the call joining virtually is David Craig and Janet Rhodes, consultants to the CEC. Thank you.
Thank you, Mr. Weaver.
Next is the Residential Consumer Intervenor Group.
Good morning. I'm Chris Oakley, representing the Residential Consumer Intervenor Association, and joining me virtually is my colleague Abdul Rahman Abo Majid. My name is spelled O-A-K-L-E-Y, and I could spell Abdul's as well if you would like. He probably won't be asking questions, though.
Thank you, Mr. Oakley.
Next is the British Columbia Old Age Pensioners Organization, Council of Senior Citizens Organization of BC, Active Support Against Poverty, Disability Alliance BC, and Tenants Resource and Advisory Center. There's a virtual attendee who's, I think, muted.
Good morning. Can you hear me now?
Yes, we can. Thank you.
I apologize. My name is Irene Elise. Last name spelled M-I-S. I'm here on behalf of BCO-APO. Thank you.
Thank you, Ms. Miss.
Are there any other interveners who have not called for the appearance? I don't see any, Madam Chair.
Thank you, Mr. Brusely. Now, BC Hydro, I believe.
Thank you. Thank you to the chair and panel members. My name is Katrina Nilsson, N-I-E-L-S-E-N, and I'm the project manager for this project. With me today, I have Mike Beatty to my immediate right, spelled G-U-I-T-E, and beside Mike is Ming Su, spelled S-O-U.
Thank you, Ms. Nixon.
So before we start, I would like to acknowledge that this meeting is taking place on the unceded traditional territory of the Musqueam, Tsleil-Waututh, and Squamish First Nations. This project, the Lower Mainland Reactive Power Reinforcement, has worked in 5 different locations in the Lower Mainland and Fraser Valley, and therefore it potentially impacts 15 different First Nations. We describe those nations and how we're engaging with them regarding the project in Chapter 5 of the application. A recent example of that is a visit to Meridian Substation earlier this month with representatives from the Coquitlam First Nation. They've got concerns about potential archaeological and environmental impacts of the small site expansion and ditch relocation we're proposing on that site. During that visit, we learned more about the nation's past use of the land, and we discussed the need for archaeological monitoring during construction. We also talked about the replanting around the new ditch that's going to take place after construction, and learned that Coquitlam is preparing a list of native plants of significance to them that we can use as input to our revegetation plan. Today we'll be working through the 4 scope items identified in Exhibit A4 and provide opportunities for clarifying questions. There may be questions that get into confidential areas, and those we're going to have to defer to written information requests. We'll do our very best to answer all your questions today, but should there be something we can't answer without going back, we may ask that the question is also raised through the written information request process. Here is the agenda for today. And after these opening remarks, Ming-Su will present the first two topics on the basics of reactive power and available technologies to control it. We've rearranged the order of those topics a little bit because it flows better that way, but we will be covering every aspect. Parts of this presentation, specifically the first two topics, are very technical, and we recognize that they may not be the easiest for everyone to understand. We've done our best to present the information in an uncomplicated way, but if you need further clarification, please ask. We built pauses into the presentation for questions for that specific purpose. After Ming's presentation, we're going to take a 15-minute break, and then I will be presenting the first part of the third topic on the project alternatives and Burrard Synchronous Condenser Station. Then we plan to break for lunch for about an hour, and after the break, I'll complete my presentation on that third topic. And lastly, Mike Guite will present the fourth and last topic on the project relevance in the context of the additional load forecast. Before I hand it over to Ming, I want to start us off with a quick introduction to why we need the Lower Mainland Reactive Power Reinforcement Project. The project is needed to manage reactive power on BC Hydro's transmission system to achieve three different objectives. The first one is maintaining transfer capability of the interior to Lower Mainland transmission system. Secondly, we have to maintain voltage control for the Metro Vancouver regional transmission system. And third, we have to relieve voltage constraints to support load growth in the Central Fraser Valley regional transmission system. Today, we rely on the Burrard Synchronous Condenser Station to supply reactive power to the transmission system to meet the first objective on that list, maintaining the transfer capability of the ILM system. We also rely on Burrard to absorb reactive power to meet the second objective on the list, maintaining voltage control of the Metro Vancouver system. And while that's working relatively well today, the Burrard facility is around 60 years old and deteriorating. So we need to either invest in upgrading it or replace its function with something else. At the same time, we're seeing load growth in the Central Fraser Valley. That means that we also need to be able to supply additional reactive power to support the Fraser Valley system, which is the third objective on the list. With this project, we address both the aging Burrard facility and the load growth in the Fraser Valley. And with that, I'm going to hand it over to Ming to present on the first two topics. Ming, please go ahead.
So can you hear me? Okay, thank you. I'm going to introduce the reactive power and reactive power compensation, the concept, and those concepts are the foundation of this project. It's getting a little bit technical, but I will try my best to explain in plain language so that you can easily understand it. Next slide, please. So this Lower Mainland Reactive Power Reinforcement Project is all about reactive power planning. And before we dive into reactive power planning, I'd like to introduce some fundamental concepts in power system so that we can gradually dive into this project, why we are doing this project. Okay. So the alternating current flowing through an electrical system has two main components. One we call active power, another one we call reactive power. They constitute what we call apparent power and the total power flowing through the whole power system. Active power provides the energy consumed by the electric equipment. It's measured in watt, kilowatt, and megawatt. Active power lights the lights. It produces the heat we need, and it turns the motor on, so it's relatively easy to understand. Reactive power. It provides the transfer of active power through the system to the electric equipment, where the magnetic field and electric field created by the AC system. We sometimes call it imaginary power, and is measured as var, kilovar, and megavar. The last concept we call apparent power is the combination of active and reactive power. Next slide, please. So, on the first slides, we work through the three fundamental concepts: active power, reactive power, and apparent power. For active power, I briefly introduce how it works and why we use it. I think you can understand it. But for reactive power, I just simply read the definition. On these slides, I will walk you through the reactive power to see how it works, why we need reactive power, and why we have to compensate it. Because it's a relatively complicated concept than the active power. That's why I try to break down the concepts piece by piece to introduce to you. Okay. So first of all, what does reactive power do? You can take a look at this diagram. This diagram is a simple diagram to show the whole power system. It's a simplified one from a hydro generation to step-up transformer, transmission line, step down to the substation, and then to the end user. So this is a simplified power system diagram. Now, on the generation side, for hydro generation, we use the water as the energy source. Water drives turbine. Turbine connects to the rotor, it rotates. But if you look at this diagram, there's an orange circle between the generator rotor and the generator stator. Those we call the air gap. And between the generator rotor and generator stator, there's no connection. So how can the energy transfer from the water turbine, the rotor, to the stator? Through a magnetic field in the air gap. Who created magnetic field? Reactive power. Now, energy generated from the generation goes to the transformer. Step up, step down. Now take a look of transformer. This is a simple illustration of how transformer look like. Transformer has a primary winding, has secondary winding, and this is the magnetic core. So if you look at this one, between primary winding and secondary winding, there are no electric connection. So how can we transfer the power from primary side to the secondary side? Through the magnetic field. Who created magnetic field? Reactive power. Now let's take a look of the end user. At our home, we use a lot of compliance, electric compliance. We use refrigerator, we use washing machine, we use dryer. Some homes have air cons. Those electric appliances look differently, but they have a common part inside those appliances, what we call induction motor. It looks like this one. So the induction motor works is we get electric energy through the stator, and this is a rotor drive the mechanical load. But how can the energy transfer from stator to the rotor? Again, they through this air gap, and between rotor and stator, there are no connection directly. So we just through this magnetic field. Again, reactive power created those magnetic field. Now we know what reactive power does. It provides the transfer for the active power consumed by the end user all the way from generation through the transformer, through the transmission lines, step down to our end user. Without reactive power, system will not work. That's how the reactive power does. The second concept I'd like to introduce is we need to understand what are the source of reactive power and what are the sinks of reactive power. In a power system, the source of reactive power are generations. It provided the reactive power and active power to serve the whole system. What are the sinks of the reactive power? As I mentioned, the sink of reactive power is the end user, is our load. Load absorbs the reactive power, load also consumes active power. The sink of the reactive power also includes the transformer because it absorbs the reactive power to build up magnetic field. After that, let's take a look of how the reactive power moves, how it flows. So before we talk about reactive power flow, let's talk about real power flows. For the real power flows, it's relatively easy to understand. We have the end user here, we have a generation here, and we need to transfer the real power, what we call the active power, to the end user. It's a one-way street. Generation generate active power, transfer to the end user, is consumed by the end user. It basically converted the active power to other form of energy, from electric energy to the light, to the heat, and mechanical energy. However, the reactive power is bidirectional. Half of the time, reactive power helps to build up the magnetic field, generator, transformer, and end user. Half of the time, it releases the energy back to the source, which is the generator. So it's sloshing it back and forth, but it never goes out of the system. It does not consume by the end user. It's only between the magnetic field and the source. Therefore, another name, or people call it wattless power. Basically, it does not consume megawatt. It's only transferred between the magnetic field and the source. So this is how reactive power moves. Now, the next concept I'd like to introduce is why we have to compensate it. Can you touch the fly-in, please? Thank you. We have two considerations why we have to compensate the reactive power. Let's refresh our mind. For the source, reactive power source, we use generator to generate reactive power. This is a power triangle. This is apparent power. This is active power, which we use to consume by the end user at our home. This is part of reactive power. Given a generator, every generator we have a fixed capacity. For example, if one generator rated 100 MVA, it can generate some amount of active power which we use consumed by the load, by the customer. It's also capable to generate some amount of reactive power. But from utility perspective, we try to generate as much active power as we can to serve the load. Therefore, we try to reduce this portion. We don't want to generate too much reactive power using generation. This is on the generation side consideration. Another consideration is on the transmission side. These two towers represent a transmission system. But take example of BC Hydro transmission system. We have the 500 kV transmission system all the way from Peace region to the lower mainland. So these two towers represent 1,000 kilometer transmission system. So every transmission path, we have a certain limit that you can only transfer this amount of power. Let's take a look at this. If a transmission system have a fixed apparent power transfer, and what we want to do is we try to transfer as much active power as we can to serve the load. We don't want the transmission system to transfer too much reactive power because it can occupy the whole capacity of the apparent power transfer through the transmission system. So we try to minimize the transfer of reactive power. How can we do that? we compensate those reactive power. Now let's refresh it. The sink of the reactive power, as I said, is the end user, is the load. BC Hydro, the peak load is around, the big number is 10,000 MVA. This is BC Hydro maximum load. Now, the reactive power part is around 2,000 megawatt. Those are the lower mainland. Majority of 70% of BC Hydro load are in lower mainland. So how do we compensate this 2,000 megawatt absorption from the low mainland load? We do local compensation so that we don't need the generation as far as in the Peace region or Columbia region to generate too much reactive power. We don't need a 1,000-kilometer transmission system to transfer 2,000 megawatt reactive power required by the end user. We locally compensate. That's why we introduced the next important concept, which is the foundation of this lower mainland reactive power reinforcement project. Next slide, please. Is we call reactive power compensation. It's the importance of reactive power compensation. So reactive power compensation is a methodology used to control the reactive power flow so that it can introduce the overall system performance. It's helping us. It serves the following four major objectives. The first objective it helps to regulate the system voltage. People may ask, what if we don't regulate the system voltage? What will happen? So in power system, each equipment, even including at our home, we have a certain operating voltage range. We have an upper limit, we have a lower limit. Upper limit typically is based on 110% based on nominal voltage, and the lower limit is 90% based on the nominal voltage, minus 10%. You may ask, what if I go beyond 110%? What will happen? The simple answer is it may potentially damage the equipment, damage equipment insulation. Another question people normally ask, what if voltage go low, a little bit low, what will happen? So the simple answer to that is, if the voltage is low at your home, your personal computer may get kicked out, your refrigerator may stop working because the induction motor will stall. On the industrial side, the industrial motor will stall, the industrial process will be interrupted. That's why when the voltage go low, that's what will happen. So reactive power compensation help to regulate the system voltage within the acceptable range. That's the first objective it serves. The second objective it serves is reactive power it increased the transfer capability. As I already introduced, in BC Hydro, we have a long transmission line, almost 1,000 kilometers from Peace region to Lower Mainland region. Right now, we have 3 500 kV lines. We call it backbone system from Peace region to Lower Mainland to serve the load. But each transmission pass, it have a limited transfer capability. If we can build unlimited transmission line, yes, of course you can do that, but the reality is we cannot. So we have to maximum use the existing transmission system. How do we do that? We use reactive power compensation, try to increase the transfer. The next one is we also use reactive power compensation to maintain the system stability. System stability is a rather complicated concept. It includes a lot of sub-concepts such as voltage stability, frequency stability, and rotor angle stability. I won't go to that depth, but in a nutshell, what does it mean maintain system stability? Is for a power system, given a certain operation condition, initial conditions, if the system is being subject to a physical disturbances or multiple disturbances, and can still regain or reach a new set of equilibrium set, and the system remains intact, then we call this system is stable. I think some of the people you may remember back to early 2000 in eastern US, we have a big blackout and people without power for several days. There are even casualties happen. That we call a blackout, instability system. We don't want this thing happen in BC Hydro system. So reactive power compensation provides the capability to maintain the system stable. It's very critical. The third objective reactive power compensation does is it has to compensate the reactive power demand. For example, in the Lower Mainland and Vancouver Island, it contains 70% of BC Hydro load. And we don't want the generation in the Peace region or in another big generation cluster in Columbia region to transfer a lot of reactive power to the load center. Therefore, we locally compensate the reactive power demand. By compensating the reactive power demand, we reduce the reactive power transfer through the transmission line. Therefore, we reduce the losses and we increase the efficiency. The real power losses is a dollar value, and we have to pay. Ratepayer has to pay. So we try to reduce the real power losses, what we call active power losses. The last one, but not the least one, is by doing reactive power compensation, we can maximize utilization of the existing transmission facilities like the transmission lines so that we can defer the construction of new transmission lines as long as it can be. Next slide, please. Any questions on reactive power? No? Next slide, please. Now, I'd like to introduce the reactive power compensation technologies to all of you. We categorized reactive power compensation technology to two different groups. The first group, we call it conventional compensation equipment. The reason we call it conventional because it's just the fundamental elements used in the electric system in the past 100 years. So it consists of mechanically switched shunt capacitor, mechanically switched shunt reactor, synchronized condenser, and series capacitor bank. Utilities start to build high voltage transmission system in 1930s. When I say high voltage transmission system, the definition of high voltage transmission system in power system is any voltage level higher than 100 kilovolts. In Europe, in North America, we start to build high voltage transmission in 1930s. So people start to put in switched shunt capacitor bank and switched shunt reactor to compensate the transmission system. In BC Hydro, we start to utilize mechanically switched shunt capacitors in 1980s. In BC Hydro, we start to utilize mechanically switched shunt reactor in 1960s when we built the 500 kV backbone system from Peace region to Lower Mainland. We try to compensate the 500 kV line charging. The synchronous condensers, the earliest history I can find is GE put in the first synchronous condenser back to the 1920s. In BC Hydro, we start to install synchronous condenser back to the 1950s when BC Hydro constructed the HVDC system from the Lower Mainland to serve Vancouver Island load. The series capacitor bank, only utility started to use it when utility built actual high transmission system. We define actual high transmission system is anything above 287 and 330 kilovolts. The first application of series capacitor bank is starting in Europe, in Sweden. They installed the series capacitor bank station on their 330 kV system. In BC Hydro, we start to use series capacitor bank in 1960s, concurrently when BC Hydro constructed 500 kV system from Peace region to serve Lower Mainland load. The next group of the reactive power compensation technology, we call it flexible AC transmission We also have an acronym called FACT devices, F-A-C-T, FACT devices. This type of technology or equipment are basically controlled by the power electronic devices. The first subset of FACT devices is called terrestrial controlled equipment. The successful utility application starting 1960s in Hydro-Quebec, they install massive amount of static walk compensator on their 735 kV system. In BC Hydro, we installed terrestrial controlled static walk compensator in 1990. The second subset of flexible AC transmission system, we call it voltage source converter basic equipment. It was invented in late 1980s concurrently by a professor in McGill University and a doctor in Siemens Company. They concurrently published a paper of application of voltage source converter on HVDC system. Sooner that people found out this voltage source converter technology can be used on reactive power compensation. BC Hydro started to utilize voltage source converter based reactive power compensation technology in early 2000. Next slide, please. Let's go over with the conventional reactive power compensation equipment. The first equipment I'd like to introduce, we call mechanically switched shunt capacitors. Shunt capacitors are connected in parallel. In parallel means this is shunt capacitor. In parallel means in parallel with the transformer serving the load and with other transmission lines. It supports reactive power and increase the system voltage. It's very effective to raise the voltage. As long as you close this we call circuit breaker, the voltage will rise so that we can keep the voltage within acceptable range. It has relatively lower capital cost and operating and maintenance cost. We call the OMA cost. It's a pretty reliable equipment. It's a static equipment. Once we put it in, with occasionally inspection, the system can last more than 20 years. It's very reliable. The cons of mechanically switched shunt capacitors are also obvious. Those are passive equipment. We need to specify certain settings to switch it in. So it has relatively slow response. We need to leave some threshold and also some delay. Typical response time for mechanically switched shunt capacitor bank is around 5 seconds in BC Hydro. Mechanically switched shunt capacitor bank cannot continuously regulate the system voltage. For example, if a shunt capacitor bank rated at 100 MVA, you switch it in, it gives you 100 MVA capacity. It cannot give you from 0 smoothly to 100 MVA. That's a discrete control. It's not continuous control. The mechanically switched shunt capacitor, the output is impacted by the system voltage. The mechanically switched shunt capacitor, the rating is proportional to the square of the system voltage. So if the system voltage drops to 95% of the nominal voltage, the mechanically switched shunt capacitor bank will drop to 90% of its rated capacity. That's the drawback of mechanically switched shunt capacitors. Next slide, please. Mechanically switched shunt reactor has similar pros and similar cons. The only difference is provide the reactive power support by lower the system voltage. It's just exactly the opposite way of reactive power compensation, which I just mentioned the capacitor does. I won't go into details. Next slide, please. Synchronous condenser. Synchronous condenser is a synchronous motor running without mechanical load. That means you don't put the load on the shaft. You just run it. It can generate or absorb reactive power like a synchronous generator like I showed, hydro generator. It can generate reactive power. It can generate absorb reactive power. The advantage of utilizing synchronous condenser is it provides continuous water regulation. If a synchronous condenser is rated 100 megawatt, it can smoothly give you from 0 to 100 megawatt. The output of synchronous condenser will not be impacted by the system voltage, not like shunt capacitor bank or shunt reactor. If the machine is rated at 100 megawatt, no matter how low or how high the system voltage will go, it will always give you 100 MVA, the rated capacity. Synchronous condenser can increase the system inertia. People may ask, what does that mean, increase system inertia? In a nutshell, you can think about increased system inertia means the synchronous condenser has a shaft. It can help the system to regulate the frequency. In North America, we run at 60 hertz. 60 hertz means in one cycle, the AC current changes 60 times of the direction. In BC Hydro, we have a strong 500 kV transmission system. We have a lot of generation. We also interconnected with United States. So our frequency control is not an issue. But in some utility, in some part of the world, they do encounter the frequency deviation problem with recent solar farm and green energy, like in South Australia. They did install synchronous condenser back to 2019, try to control their system frequency. The next advantage of using synchronous condenser is it contributes to the system short circuit capacity. It's a machine. Anywhere there's a fault, this machine can contribute the short circuit current to that fault. What does that mean is, if you connect the synchronous condenser to this bus, it will reduce the voltage fluctuation if there is any adjacent fault or disturbance. This machine can control the voltage at this bus. It's a machine, it has overload capability. It can overload up to 20 to 30 minutes, very strong capability. The cons of synchronized condenser, it has a moderate response speed. Because it's a big machine, it has a rotor, it has an inertia. Take example, for barrage, it takes around a second to respond to the system disturbance, 1 second. It has a relatively higher capital cost. It has relatively higher operating and maintenance cost. It has a higher losses because it's a machine. The megawatt, the active power losses can run up to 5%. So if a machine is rated 100 MVA, if you're running at the full capacity, you lost 5 megawatt right away. It has relatively lower reliability because it's a rotating part. You need to do the maintenance, same thing like we do the oil change for our car. Next slide, please. The last conventional type of the reactive power compensation technology we call is series capacitor. So what it does is we typically insert series capacitor in the middle of transmission line, try to reduce the transmission line impedance. The impedance is the opposition of alternating current, AC current, presented by the combined effect of resistance and reactance of a circuit. It's the most effective way to increase the power transfer capability. It has been used in almost all the utilities that have long transmission lines. How can it effectively increase the power transfer capability? In a nutshell, the power transfer function is in reverse of the line impedance. So if we can theoretically reduce the line impedance to half, then you can double the transfer. How can we reduce the line impedance to half? We insert the series capacitor bank. It effectively reduces the line impedance. Physically, if BC Hydro transmission line is 1,000 kilometers from Peace region to Lower Mainland, we want to make it run like a 500-kilometer long transmission line. How can we do that? We seriously compensated all the 500 kV lines, insert a series capacitor bank. In planning domain, we normally call 50% compensation. 50% means it's 50% equivalent to the transmission line impedance. Therefore, it effectively reduces the reactive power losses along the transmission line because you just compensate the reactive power losses by series capacitor. It's a self-regulated equipment. It's not like the shunt-connected equipment. The shunt-connected equipment, as I just said, you have to give a setting, give a timer. You have to properly study that. The series capacitor bank, once you insert it, is a part of the system. It self-regulates itself. The cons of series capacitor is because the ideal location is always in the middle of the long transmission line. It's typically in the middle of nowhere, so it's not easy to gain the access. It has a relatively higher capital cost. Series capacitor bank is we have to build a brand new substation. It's not like the shunt equipment, you can install it within the substation. This is a brand new big substation. Therefore, it has a medium operation and maintenance cost, and it has a long project lead time because you have to acquire the land if you have to build a brand new substation. Next slide, please.
Sorry to interrupt, but
Sure.
Mr. Joe,
Yes.
can you put in the series
Can you?
capacitor
Yep.
after the transmission line has already been built?
Yes, you can.
So anytime during the life of the transmission line, if you decided that was the appropriate mechanism to deal with reactive power, you could actually insert the series capacitor.
Yes, we can.
Okay, thank you.
While we're asking questions, can you speak about the advantages of a self-regulating system versus, the other three that we heard about, the more mechanical ones? What are the advantages of self-regulating? Thank you.
Sure. The self-regulated reactive power equipment, I think so far what I know is the series capacitor bank is the only one can be inserted. The other one all shunt connected, so you have to specify a setting. The advantage of series capacitor, which is self-regulated, is once you put it in, it's regulated based on the system, the power flow flowing through the series capacitor bank, also the system voltage between the series capacitor bank. We normally don't need to interrupt unless there's something happen, there's a fault happen, we have to switch it out. Otherwise, we pretty much leave it as part of the transmission line to operate. But shunt capacitive equipment, you have to connect in parallel. You have to determine at what moment you need to switch those things in, at what moment you need to switch it out. For continuous operating equipment like synchronous condenser, you can connect it at all the time, but you need to give a proper voltage setting so that it will not go to next seconds goes to a maximum 100 megawatt, and after next second go to a minimum capacity, minimum capacity. So we always have to properly study that and provide proper setting for the shunt equipment.
Great. So in other words, it automatically responds to the MVAR-related needs of the transmission system, as opposed to having to identify a system in parallel that, design it to respond appropriately. It automatically responds to the reactive power.
Yes.
Thank you.
Next slide. So, flexible AC transmission. Those are electronic-based facilities that provide control of one or more AC system parameters, such as voltage, impedance, and others, to manage the reactive power flow. The first type of FACS devices we call terrestrial controlled facilities. the most common application for terrestrial control equipment we call static wall compensator. The acronym is SVC. The second type of terrestrial control facility we call terrestrial controlled series capacitor. BC Hydro does not utilize this technology because this technology normally used by the utility that have coal-fire generation and long transmission lines. The second subset of flexible AC transmission is voltage source converter-based facility. The most common used technology we call static synchronous compensator. The next one we call static series synchronized compensator. Again, this static series synchronized compensator typically used by the utility that have coal-fire or thermal generators with long transmission line. In BC Hydro, we have hydro units, so we don't utilize this technology. And various combination between static series compensator and static series synchronized compensator. Next slide, please. Let's take a look of static wall compensator. It's a combination of terrestrial controlled reactor and terrestrial switch capacitor connected in parallel to regulate the voltage. Take a look at this station diagram. If you don't look at this switch, this is just the same as mechanical switch reactor and mechanical switch shunt capacitor. But we add those valves, try to control the current flowing through the shunt reactors so that we can provide a smooth control other than switch it in at 100%, switch it all at 100%. So this one gave you flexibility to provide a continuous control smoothly and also give you very fast response. Those terrestrial can switch up to a kilohertz. That means in 1 second it can switch 1,000 times. So it's a fast response switches. It provides very fast voltage regulation. SVC, we call static wall compensator, can typically respond in 5 cycles. Cycle means in North American, we're running at 60 hertz. 1 cycle is around 16.67 milliseconds. So 5 cycles is around, in 100 milliseconds, SVC can kick in and regulate the voltage. It provides continuous voltage regulation smoothly from 0 to the rated capacity. Therefore, it enhances the steady state voltage control, and also it will help to provide the transient stability control. Hydro-Quebec use SVC to provide the transient stability control for their big generators. The cons of static wall compensator is the output is still impacted by the system voltage. If you look at this, this is still a reactor and capacitor bank, which means if the system voltage run low, you still have the output of SVC will be impacted by the system voltage. It has a medium capital cost because you have this portion, this additional portion compared to purely mechanically switched shunt capacitor and mechanically shunt reactors. It has medium operating and maintenance cost because you have those moving parts, and moderate reliability because you have to properly maintain those terrestrials. It's a moving part. It's doing the high-speed switching in and out. Next slide, please. Static synchronized compensator. It accomplished the same effect as a static wall compensator, but instead of using capacitor bank and reactor, it just used a voltage source converter like this one with a battery bank or DC bank to synthesize a voltage waveform of various magnitude with respect to the system voltage change. What it does is, this is the substation bus. If there is an adjacent system disturbance cause this bus voltage drop 10%, this equipment will sense that 10% voltage drop and produce exactly 10% magnitude voltage injected at this point. So this is how it works. It does not rely on any reactors or shunt capacitor bank. All the relay is this one. It's a DC bank plus a converter, a voltage source converter. It provides super fast response. Those voltage source converter, they use different type of the switch. They call it IGBT. I think the full name is insulated bipolar gate transducer. I'm not an expert on those equipment, but the chopping frequency can go as high as 10 kilohertz per second. So it's almost 10 times faster than the terrestrial. This type of equipment can react to any system response in 1 cycle. That means in 16.67 milliseconds, it can respond. It's super fast. It provides continuous water regulation. It's smoothly from 0 up to the maximum capacity. It has some short time overload capability. It can do a few minutes overload, like 120%. Output is not impacted by the system voltage because they have their independent voltage source here. So it can always give you the rated capacity. The cons of static synchronous compensator is it has a relatively higher power losses because those high-speed switch, they always work all the time. So they always do the switching. There are a lot of heat dispatch. You have to dispatch the heat. Otherwise, it's very fast switching. It has a medium capital cost because of the voltage source converter, these modulars, and medium operating and maintenance cost because those are moving part. They always switch in and out, in and out. Therefore, it has a moderate reliability. You have to do a proper, maintenance in order to keep it reliable to operate. And this type of modular has a relatively short life cycle because once you connect it to the system, it always switch in and out. So typical life cycle is between 10 to 15 years. After that, you have to replace those modules. And if you buy from one vendor, you cannot go to the other vendor. It's very specific equipment. You have to go back to that vendor to get those replacement. So those are the speciality of the static synchronous compensator. Next slide, please. I summarize the shunt reactive power compensation devices in this table. I didn't put in the series capacitor bank because it does a different job. It's like compare apple to banana. So we're only here to compare the shunt reactive compensation devices. At least the technology, control mode, capacity output, response time, capital cost, OMA cost, reliability, and losses. Each type of equipment serves their own purposes for the specific application. Green means it's good. We like to see green. A little bit red means it's a bit higher cost for the synchronous condensers. But as I said, it all depends on the application. In the South Australia area, they installed 4 synchronous condensers back to 2019, purely try to help to regulate the frequency. There's nothing else you can do except synchronous condenser. So each equipment, if you need super fast response like SVC, static Watt compensator, or static synchronous compensator, if you need really fast response, for example, if we have a load, an arcing furnace load around, you don't want to see your light bulb flick all the time. You put in those fast response equipment. If you have a stability problem, in few cycles, the system may run into stability like HVDC. You may try to implement those type of equipment. So each shunt reactive compensation device serves their functions on their specific application. Next slide. Any questions on available technologies?
Good morning. My name is Graham McGillivray. That's MacGillivray with the BCUC staff team. I do have some questions on the basics of reactive power, just to take a step back. First, you spoke to the impact of low and high voltage conditions on customer loads, but could you please elaborate on the impact of low voltage and high voltage conditions on the transmission system as a whole?
On the transmission system, we plan the transmission system based on the North America Reliability Council, we call it NERC, or Western, we call it West WECC WEC. We have a planning standard for system normal operating conditions. We allow 5% plus or minus voltage deviation. 5% means on the normal condition, you allow to go 105%. Low voltage, you're allowed to drop to 95% of the nominal voltage. Those are the system normal operating voltage range we allow by the WEC. On the single contingency, we allow to go as high as 10%. This goes up to 110%. And we allow it to go as low as 90% of the nominal voltage per WEC planning standard and performance criteria.
Great, thank you. Next, I'd like to understand the concept of power factor. Can you please explain what the distribution load power factor is, how it relates to reactive power, and what it means to approach unity?
Sorry, what it means to?
Approach unity.
Okay. So power factor is the ratio of active power to apparent power. If you remember that triangle, it's a ratio of the active power to the apparent power. This one. So from utility side, we always expect if the load, the customer load on distribution load, if we can reach higher power factor, where I mean higher means close to unity, close to 1. But typical distribution load power factor in the past is around 0.95 lagging. Lagging means is most of them are inductive load. And in the recent years, the distribution load power factor we have observed gradually improve. Maybe because of we use a lot of converter-based load in our home, at our home. So the power factor gradually improved close to unity, between 95 and unity. In terms of the impact of power factor, distribution load power factor to the reactive power compensation is, as I just mentioned, BC Hydro has a peak load or maximum load around 10,000 MVA. 70% is in Lower Mainland, around 7,000. Based on the rough power factor distribution load is around 0.97. The reactive power demand in Lower Mainland Vancouver is around 1,500 megawatt. And what we do is, in order to compensate those 1,500 megawatt reactive power demand from distribution load, we try to locally compensate those demand in the Lower Mainland region, try to compensate those distribution reactive power demand. Those on the transmission side. We also directly install the compressor bank on the distribution level, try to provide certain compensation. So there are different level of compensation and try to improve the whole system performance.
Great, thank you. Next, can you please discuss the circumstances that have caused the power factor approach unity, specifically in the Fraser Valley regional transmission system?
Sorry, can you repeat your question?
Sure. Can you please discuss the circumstances that caused the power factor to approach unity, specifically in the Fraser Valley regional transmission system?
Okay. So in the Fraser Valley area, we see some amount of load growth higher than the other region. What we found out is under certain system conditions, or I say under certain system contingency conditions, that the system voltage will go lower than the criteria requirements such as -10%, and those are partially caused by the load growth in the Fraser Valley area. When I mean load growth means the load, not only the actual power load increase, also the reactive power demand also increase. So that's why in the Fraser Valley area, we observe that in order to accommodate those load growth, both active power and reactive power, we have to put certain compensation in the Fraser Valley area and try to meet certain performance criteria defined by the WAC and defined by the NUC.
Great, thank you. So next, can you please explain how dynamic or how variable this power factor is?
I mean, what you mean is dynamic response or power factor itself?
The power factor itself. So with respect to, say, over time, how often is the power factor changing? Is it?
In planning domain, we normally use a fixed power factor to do the planning. For example, in the past, we typically use 0.95 lagging and do the planning. But I just mentioned a few minutes ago, we have observed that power factor improvement in the past few years from distribution, from the metering smart meter. And we gradually modify those power factors in our planning work. So as you said, the power factor is gradually improving, but I believe what you ask is different than the actual power factor. The actual power factor is always dynamic. There's no fixed one. It's always fluctuating. But I think what you mean is when in the planning domain, we use the different power factor to the planning. Yes, we do use it. In the past, it's a little bit lower, around 0.95, but right now we gradually try to improve the accuracy of the data and try to reflect the reality.
Okay, great. Thank you. Next, I do have a few questions related to the available technologies. In order to understand how common shunt reactors, capacitors, and synchronous condensers equipment are, can you please explain how many of each type in relative terms, if you don't have exact numbers available, how many of each type of equipment BC Hydro has in its power system?
Those information I will provide in the next few slides. I can briefly introduce here. We, in BC Hydro, we apply almost all technology in our transmission system. We have installed 230 kV shunt compressor band, 500 kV shunt reactors, 230 kV shunt reactors. We installed the SVC, we installed STATCOM, we installed the synchronous condensers. You name it, we install almost all kind of technology in BC Hydro. I'm going to introduce it in the next few slides when I show you the map, so you can have some rough idea where we install it and approximate amount of those equipment and the purpose why we install it.
Perfect. Thank you very much.
No problem.
Mr. Joe, I do have a follow-up question. This is Commissioner
Yes.
Fung speaking. Based on Mr. McGillivray's last question, and that is, moving forward, based on your experience with all these types of technologies on your system, is there a plan going forward with respect to what BC Hydro is planning to do from a trend perspective in terms of focusing on one or more of these technologies? Or does it vary depending on where you are in your system and what we're talking about?
It depends on where is the location and the purpose to serve the system.
Okay, thank you.
Just while we're in the kind of the basics, could you comment on the differences in types of loads, for example, in buildings in the distribution grid with respect to both reactive power demand and, adding reactive power onto the grid? So the difference, for example, between resistance heating, conventional water heaters versus emerging technologies such as heat pumps that have a motor, including heat pump water heaters or even space heaters. Is there a difference? And, you know, given the proliferation of heat pumps in British Columbia, is there a change in the need for MVAR control as a result of those types of loads being more prevalent versus the last few decades that have been, you know, more focused maybe on resistance heating? And similarly, are there industrial loads, for example, that are exacerbating reactive power control needs? Thank you.
So let me answer the first question about residential load, the trend of residential load. I'm not an expert on distribution load, but I will try my best to answer. So what we observed is previously, like you said, we use resistive heaters. We use a lot of this type of non-effective equipment. Now a lot of residential load, even at my own home, we use heat pumps. What we observed is from the distribution meter is the power factor gradually improved from the previous decades, or even 30 or 40 years ago. Low power factor, when I say low, is around 90% to 95% lagging, means inductive, towards unity, basically close to not inductive, not capacitive. That's the trend we have observed. I can't answer the question if this is because of the heat pump, but my guess is this is because of the residential load. People start to use a lot of appliances with converters and more energy effective stuff. Therefore, it changed the distribution power factor. It basically improved it. In a way, it helps the transmission system. So from utility perspective, we always like a higher power factor or close to unity power factor, but that is we have observed, which is good trend. If people start to use this thing, it's also going to benefit utility to compensate the less. A big number is, if we still, based on the previous decades of old power factor distribution load, let's say 0.95 lagging, for a peak BC Hydro load 10,000 MVA, we almost have to compensate 3,000 megawatt reactive power. But with improved power factor, let's say 0.98, you only need to do half, 1,500. So it's greatly improved the system performance from distribution side, from the residential side, to help the utility to regulate the system. Now, in terms of your second question about transmission customer, BC Hydro, we have electric supply agreement with each transmission customer. Our requirement stipulate very clear in the ESA is they cannot go below 95% lagging. I think we all know that residential load, when we receive the bill from BC Hydro, Hydro only charge active power consumption. We don't charge reactive power absorption. But for transmission customer, we do monitor the reactive power absorption from those big industrial customer, and if we see the excessive one beyond acceptable range specified in the ESA, then I do believe in the BC Hydro for commercial or for the industrial customer, we do have to charge on the reactive power demand.
Great, thank you. And final question is the bottom row of the comparison chart on the previous slide. And just if you could comment further on the overall transmission system losses. And so, what's the difference between high and small in terms of the impact on the overall bulk electric system transmission losses? Is there a measurable benefit to these emerging and newer technologies as we shift from red to green? Thank you.
Okay. So I assume when you say the losses is the equipment itself losses, it's not mean to the transmission losses reduction. So if my understanding is correct, is let's take example of a synchronous condenser is high. High means it can go as high as 5% of the machine rating. Negligible like shunt capacitor bank, it doesn't really cause any active power losses, so it's almost zero. Static synchronized compensator, we rate is high because it has high chopping frequency. It's like 10 kilohertz level, so it creates a lot of heat. And the power losses on that specific equipment can range between 2% up to even 7%. This is based on the literature. BC Hydro also have the application of those type of technology. So those things does absorb the actual power, basically consume and transfer to the heat. Small to negligible is we call static Watt compensator. It has some low frequency switch, so it's not as high as 10 kilohertz. Therefore, it does not consume that amount of active power. So we would categorize it as small to negligible for the static Watt compensator. All this equipment, once we put it in, it will reduce the transmission active power losses. So to answer your question from the other perspective, all the equipment, they will reduce the power losses. This green and red only refers to this specific equipment losses. Thank you.
Great, thank you.
Okay, Mr. Joe, it's Commissioner Fung speaking. Just want to follow up on your recent discussion about improved power factor. Can you tell me whether your observation about improved power factor applies equally to the transmission system and the distribution system, or is it an observation that's limited to one or the other?
Only on distribution system.
Only on the distribution system?
Yes.
And I just want to understand the implications of this in terms of of the need to invest in regulating reactive power. If I understood the discussion correctly, if you have an improved power factor, that means that whatever you're doing right now to manage the reactive power situation suggests that what you're doing is adequate. Is that correct?
Yes.
So there's less need to provide reactive power compensation when you have a higher power factor.
In a way, is correct.
Okay, thank you.
Okay, next slide. So let's talk about the role of reactive power in BC Hydro system. We already mentioned that reactive power compensation can help to regulate the system voltage, increase the transfer, maintain the stability. So what does it mean from planning domain? When we plan the transmission system, what do we consider? In the planning domain, we normally consider two extreme scenarios. One is during the peak load or maximum load scenario. One is during the light load or minimum load scenario. As long as we cover these two scenarios, anything in between should work perfectly. Now, take an example for the peak load period, for interior to low mainland system, 70% of BC Hydro load. What reactive power does is it increases the transfer capability from Peace region, from Columbia River region. It provides water regulation to the low mainland system. It maintains this voltage stability of the whole lower mainland Vancouver Island system. During the light load period, minimum load, what reactive power does is, especially for the metro area, we have an underground cable system. We have the excessive charging also from 500 kV lines. So reactive power will lower the system voltage within acceptable range. So this is what reactive power compensation does in the light load period. Next slide, please. Now, this is a slide I try to answer that gentleman's question. This is the map, shows the effect of reactive power compensation on the BC Hydro transmission system. I pre-assume that you are not familiar with BC Hydro transmission system, so allow me to introduce, give you overall concept of how the BC Hydro transmission look like. Because of geographic characteristic of BC province, the majority of generation is in far north region, the Peace Canning, the SIC, and the GMS generation. And also we have Mica from Columbia River, the River Stoke from Columbia River area. Those are the major BC Hydro generation clusters. This is 1,000 kilometers away from the load center, which is lower mainland. This is around 600 kilometers away from the lower mainland and Vancouver Island. So from this map, this red line is the BC Hydro 500 kV system. Was first constructed back in the 1960s. Here you can see this is represent the series capacitor station. We series compensated all the way from Peace region to Williston, to Kelly, and up to lower mainland to serve the lower mainland load. All the 500 kV interior to lower mainland 500 kV line, all series compensated, try to increase the transfer demand to serve the load. You can see the next one is the shunt capacitor bank. We installed 230 kV shunt capacitor bank at Meridian and Ingoldorf starting 1980s. Total is around 900 megawatt. Try to provide the local support or local compensation to the lower mainland reactive power demands to the load. Okay. We have a synchronous condenser at Burrard to help to regulate the voltage, increase the transfer. We have a synchronous condenser at VIT, previously served HVDC system. Now with the retirement of HVDC, it continues to help to regulate the voltage. We also add a lot of shunt reactor. You see those blue one along the 500 kV line, try to compensate the 500 kV line charging during the light loaded scenario. We installed a static watt compensator at Dunsmuir substation back to the 1990s to accommodate the double contingency from Malaspina to Dunsmuir. If we lose simultaneously two 500 kV lines, this what SVC does, it will stabilize the northern Ireland voltage, so will not cause any voltage collapse. This is what SVC does. We also have application for static watt compensator, which is we call voltage source converter-based technology, the newest one. We install it in the regional transmission system in southern interior, North Thompson system, that's 330 kilometers long, try to stabilize the voltage stability in the regional system. We also install STATCOM in the northern region, a substation called Fort St. James. It's a long radio line, 60 kV, try to help to regulate the customer at the end of this radio line. So from this map, you can see BC Hydro applied all type of reactive power compensation technologies starting 1950s until now. Next slide. The technology considered or dismissed for the project. In this lower mainland reactive compensation reinforcement project, we did not consider fixed devices, shunt reactive compensation such as static watt compensator or static synchronous compensator, because the way we plan the system, we typically plan the system from lower cost equipment. Once the lower cost equipment meet the technical requirements, then we will not go with the more expensive equipment, because the shunt capacitor bank and shunt reactor does meet the need at most cost-effective way. That's the reason we did not consider the more expensive static wall compensator and the static synchronized compensator for this project purposes. The series compensation, we did study that and dismiss it because of the higher capital cost and longer project lead time. That's the reason we dismissed the series compensation alternative. Next slide, please. The overall impact of reactive power compensation on safety, operational flexibility, and system reliability. On safety, Burrard synchronous condenser station has moving parts and require continuous operation of 25 employees. So those 25 employees does have increased exposure to safety hazard because it's a rotating machine, wrong, compared to the shunt reactor and shunt capacitor, which is within the substation. And the benefit of shunt capacitor and shunt reactor include Hydro has the experience and knowledge of installation, operation, and maintenance of this type of equipment. We started to use this type of equipment many decades ago. And those type of equipment has no unique requirements and are very similar to the existing equipment like circuit breakers or transformers. And those equipment has no moving part and can be remotely operated and monitored. And only occasional on-site inspection will be required. Next slide.
Sorry, Mr.
Yes, yes.
Commissioner Fung speaking. On Burrard synchronous condenser station, am I correct in thinking that it's been operating for about 60 years now?
Correct.
And in that period of time, have you had safety issues with respect to the operations at the Burrard synchronous condenser station?
I would like somebody else to answer that question.
Right, my name is Lawrence Yu, last name spelled Y-U. Absolutely, there's been a couple safety incidents. The big one that I can remember from a few years back was our drainage system. We had corroding grates, and we ended up having some issues related to that degradation, and so we've gone through and had to do some immediate remediation there. So there's others as well, but ultimately this facility is operated 24/7 versus the remote operation of these alternatives here.
And did any of those incidents result in technical safety, BC making any recommendations to BC Hydro with respect to improvements or anything that's necessary in terms of changes?
I don't recall, but that's something that we can look into.
Thank you, Mr. Yu. Just on the Burrard synchronous condenser station then, Mr. Joe, can you tell me have you done an analysis of what the useful life of that station is? Because I have no sense of whether this is nearing end of life or middle of life or...
It's Lawrence Yu again. Sorry, I missed the question.
Has BC Hydro done an estimate of what the useful life of the Burrard synchronous condenser station is?
Not a useful life study per se, but from a component by component basis, we have looked at replacement and refurbishment, and generally it is a condition-based approach that we take. So based on the effort required to bring Burrard back to a level of service that's expected for the purposes of our planning criteria here, there would be required investments to refurbish that facility to that level of service.
And And have you done an estimate of what the cost of that refurbishment would be?
Yes, the project has done that.
And how much is that? So maybe,
I believe it's coming up in some future slides here.
okay, then that's fine. We can leave it for the moment. Thank you.
Great.
Thank you, Mr. Joe.
No problem. Next slide. So in terms of operational flexibility, BC Hydro, we consider as redundancy for operational flexibility when planning reactive power compensation. So what it does is when we plan the reactive power compensation equipment, we always consider redundancy from operational flexibility perspective. Other than give one single equipment, we always consider if it's possible we can give redundancy from system perspective. In this particular project, we have alternative. We can provide one 250 megawatt shunt capacitor at 500 kV versus two 125 megawatt at 230 kV. In the end, we choose 2 times 125 megawatt 230 kV to account for if one of the shunt capacitor bank out of service, you still have a remaining one to provide a service for the next contingency. Our synchronous condenser currently provide significant amount of reactive power in Lower Mainland at one location. This project provides 4 different locations, and therefore, given the operation certain flexibility to operate the system. Next slide, please. From system reliability perspective, reactive power compensation improves the overall system performance and ensure that BC Hydro complies with mandatory reliability standard defined by NERC. I will not go through one by one because I already mentioned that, increase the transfer, maintain the voltage. So what reactive power compensation does from system reliability perspective is it provides the required load demand at the most economic way, and same time ensure BC Hydro is in compliance with NERC IMRS requirements. That's the end of the slides. Questions? Sorry,
Mr. Oakley.
Chris Oakley with the RCI. First of all, let me commend you on handling a really tough technical topic the way you have. I understand how difficult that one is. Going to the more switch shunt penetration, are you concerned about setting up potential voltage collapse in the Lower Mainland?
If I understand your question correctly, your concern is that adding more shunt capacitor bank, will the system running into the instability situation? Yeah, for loss of a major element, I'm sure you've done the VQ analysis and all that sort of thing, but are you worried that if a major element drops out when you're under maximum load and maybe exporting, that you're setting up a potential voltage collapse situation? So to answer your question, in BC Hydro, when we do the transmission planning on the reactor power planning, we assess this type of equipment to see if it fits in the system need at a certain year. For now, shunt capacitor bank, it does the job and can still secure the system from stability perspective. But to answer your question is, we do perform PV and QV analysis, compare the shunt capacitor bank characteristic curve with the system curve. So as you may aware, if there's an intersection between the two curves, that means system still stable. But we do observe that in future with the higher load growth, for example, 10 years down the road, it is possible that the shunt capacitor bank the characteristic of shunt capacitance curve may not interact with the system curve. At the moment, we did plan the static Watt compensator in the long-range plan installed in the lower mainland system, try to continue to compensate the system other than build a new transmission line. So to answer your question, yes, we did. We consider both water regulation, typically does by the shunt capacitor bank, and voltage stability. Shunt capacitor bank can help, but eventually, if we really run into the voltage stability, we will require static Watt compensator to move in and to help to regulate the voltage and save the system.
Thanks. You also mentioned that you obviously have some distribution capacitor banks. Have you evaluated an alternative to the transmission capacitor banks by putting, additional shunts in the distribution system closer to where the actual consumption is?
When we did the planning study, there are two different philosophies. One is we call centralized control. One we call distributed control way. What we choose eventually, when we plan this project, we still choose the centralized control, and the reason is because this Burrard single condenser station, so far, it provides a major control to the IO-line pass, the 500 kV pass. We try to replace Burrard, so we try to have a central control of the shunt capacitor bank, the big one, other than I spread 125 megawatt shunt capacitor bank in one station, other than specify 10 times 10 megawatt shunt capacitor bank at 10 different locations, because the purpose of the condenser is during the peak load conditions, if we lose one of 500 kV lines on the IO-line pass, we need the condenser to push the wire out right away. The similar thing is if we don't have the condenser, we want to switch in those big shunt capacitor bank right away. We have the right control. By spread the shunt compensation to different distribution substations, we have to engage a lot of different issues. For example, we need to have a telecom control on all these distribution substations, and then we have to explore each distribution substation. You have the space to put in those capacitor banks. So in the end, after we evaluate that, we found out that the reality is in lower mainland area, we have very confined space in each substation. So the only substation available identified by BC Hydro is the substation that we install those shunt caps. Even some distribution substation, we found out the space is very confined. It's difficult to put the additional shunt capacitor bank in. So in the end, at the very beginning, when we start to plan the system, we define the philosophy how we want those reactive power compensation to be controlled and to serve the system.
Okay, thanks. And would you see this as kind of more of an interim solution? Like in the long term, do you think that series compensation increasing like to say 70% or something like that is on the table, or are there other solutions that would be better if your reactive power demand in the lower mainland continues to increase?
To answer your question, sir, this project to replace Burrard synchronous condenser, from long-term perspective, you can call it an interim solution. And BC Hydro indeed laid out the long-term transmission solution to serve the future lower mainland of Vancouver and BC Hydro load. What you mentioned, which is you must have done a lot of planning in your career, is we already planned it in the integrated resource plan and submitted to the commission already. In that plan, if you're interested, we already proposed to increase the series compensation level from the current 50 and 55% up to 75 to 80%. We already plan to install the big SVC. When I say big, is around 500 megawatt level static Watt compensator at our Ingledale and Meridian substation, try to control the system voltage and make sure we don't get into voltage collapse. So what you mentioned, yes, we did consider that in the long-term plan.
Okay, well, thanks. I'm not surprised, and yeah, I know I'd seen a series compensation project floating around from time to time over the last number of years, but just wondering how much time this really buys us.
This project, I think in our IRP filing, we plan to reinforce the next major reinforcement on ILM systems around, based on that time, low forecast information available generation resource around physical 33, 32 time-ish. But it could change if the study assumption changes, but it will be around 10 to 20 years. We have to put some major reinforcement on the ILM system, try to provide the future, try to meet the future low growth demand.
Thank you, Mr. Joe. And I have another question, but it's probably not for you. I'm trying to wrap my head around what 25 people do at a synchronous condenser site. I've certainly operated generators before, one hydro plant, rotating equipment, we had to take care of it. The operator would show up 4 hours a week, whether he needed to or not. And when we've got a bunch of spinning machines like this, I can't picture in my mind what anyone is actually doing on a day-to-day basis. So this may be a fundamental union issue, I'm not sure, but I cannot, for the life of me, understand how you get the operating cost of 25 people in this site. When the thermal has been all shut down, there's no need for steam engineers anymore, so I can't get it. And maybe this, again, is not for you, but I'd appreciate any kind of insight into what's driving that. And that's my last question, if anyone is able to answer that at all.
Apparently, we'll have to take that one as an IR. Thank you.
Thank you, Mr. Carpenter. Any other questions for Mr. Joe on topics 1 and 2?
I do want to flag for everyone that I'm not sure whether Mr. Joe is planning to stay for the rest of the workshop. So if there are any questions relating to either the basics of reactive power and available technologies, I would encourage people who have questions relating to them to ask that. And I believe Commissioner Andrew Pape Salmon did have a question that he wanted to pose.
Well, thanks. This is just framing for the next presentation on project alternatives. I'm curious what the current capacity, or sorry, the reactive power capacity is of the Burrard system. What's our starting point? Because we see in the reliability consideration, one of them is what is the MVAR capacity of the 4 alternatives, and we see that the preferred alternative is 375, and we'll get to that, but I'm just curious what the current Burrard capacity is. What's our starting point in terms of the available MVAR? Thank you.
Yes, Commissioner. If you ask about today, how much megawatt we can get out of Burrard, continuously is about 300 megawatt. But we have one unit down. If we have to spend a certain amount of money to fix that unit, theoretically we can get 400 megawatt continuous reactive power to support to the system, and we can get, Burrard can absorb around 200 megawatt from the system. So it's positive 400, negative 200 continuously. This is our starting point.
And actually, while we have you here, we've talked a lot about the the capacity of the transmission system and the MVA and the relationship between active and reactive power. And then the conversation talks about voltage control. So voltage being a different quantity. Is there a direct relationship? So when there's reactive power in the system, does that translate directly to changes in voltage? We had a brief conversation about the sort of plus 5%, plus or minus 5% is your goal and then you can go up to 10% in terms of voltage variation. I'm just curious, just that relationship between MVA and voltage. And I know there's some basic equations, but is there more or less a direct relationship? So as reactive power increases, the impact on voltage is proportional. Thank you.
I would say the power system is a highly nonlinear. It's not really a linear system. But to answer your question, reactive power directly related to the system voltage, and active power directly related to system phase angle. So these two are correlated. Anytime if we touch the reactive power, system voltage changes. So reactive power is bound with the voltage, and active power is bound with the phase angle. So these four parameters, when we plan the system, we run the power flow studies. Within the power flow, the two, reactive power and voltage, active power and phase angle, they always bound together. So that's how it works. I don't want to get into the equations. From other perspective, if we transfer more power, or if the system during the peak load period, we have a lot of load coming in, let's say 10,000, then the simple way to think it is it's Ohm's law. The voltage drop across the conductor is proportional to the current flowing through the conductor. So if you have more current flowing through the conductor, you'll have higher voltage drop on the conductor. That explains when the load is high or when the load is at maximum, the lower mainline voltage goes low, because based on the Ohm's law, the voltage drop is going to be a lot higher than if you have a less current flowing through the conductor. So I hope that helped too.
Yes, thank you.
Okay, Mr. Joe, I don't see any questions for you, so thank you for your presentation. And as Mr. Oakley said, you've managed to distill a very complicated topic down into manageable chunks for us. And I'm speaking as a non-engineer. I think I understand it, so thank you very much for your presentation this morning and for taking the time to educate all of us. Much appreciated. So it's now 10:49. I suggest we come back at, let me see, maybe 5 after 11, 11:05, and enjoy your break. Thank you.
Yeah, trying to stay here. Just like a parrot. I see it. Sure. So they're saying they're going to be there with their there. Power factor can't be removed. Yeah, yeah. They said they keep saying
Thank you very much, and welcome back, everyone. We are now at topic number 3, a discussion on decommissioning and remediation of the Burrard site and how it is considered in the evaluation of the different project alternatives, although it is not considered part of the project scope. Before I get into addressing each of the Commission's subtopics, I'm going to provide some general context that I hope will help frame our responses to the individual subtopics. And for those following along on the phone, I'll just mention that we're now on slide number 27. So I'm going to start with an overview of what each of the project alternatives is comprised of, including the work at Burrard we considered when comparing those alternatives. I will then talk about what we mean by stopping operations of the Burrard Synchronous Condenser Station and what work that includes. Next, I'll talk about what we mean by decommissioning and remediation of the Burrard site, noting that this work is not part of the project scope but is considered for the purpose of evaluating the project alternatives. For that, I'm going to describe the different areas of the site and what may be required for decommissioning. I'm going to explain how operating and non-operating areas have been considered, and I'm going to be defining those terms for you as well. I'm going to show the different land parcels that are associated with the site. I'll talk about soil remediation and what we know about potential requirements for that. And lastly, I'll explain the assumptions we made when estimating the cost of decommissioning and remediation. And as the last item before we get into addressing the individual subtopics, I will show a comparison of the present value cost of each of the project alternatives, including the cost of decommissioning and remediation of the operating area of the Burrard site. So let's have a look at the project alternatives. What we refer to as the Burrard alternative on the left of this slide includes a full refurbishment of the Burrard Synchronous Condenser Station. Full refurbishment will allow it to operate for another 40 years and continues to support the Lower Mainland transmission system and the Metro Vancouver transmission system. The synchronous condensers at Burrard can't support the Fraser Valley, so this alternative also includes installing shunt capacitor banks to support the Fraser Valley transmission system, initially one at Clayburn Substation and 7 years later, one at McClellan Substation. So moving to the hybrid alternative. That alternative includes a partial refurbishment of the Burrard Synchronous Condenser Station, enough to keep it operating for another 10 years. After the 10 years, we would put 2 new shunt reactors in service at Meridian Substation and 2 new shunt capacitor banks at Ingledow Substation. They would replace the functionality of the synchronous condensers at Burrard, allowing us to stop operating the Burrard Synchronous Condenser Station. As in the Burrard alternative, we would also install shunt capacitor banks at Clayburn and McClellan Substation to meet the Fraser Valley need. So moving to the substation alternative, we looked at 2 different options, what we call the Meridian option and the Ingledow option, named after where we would plan to place the shunt reactors. I'm going to start with the Meridian option, which includes installing 2 shunt reactors at Meridian Substation and 2 shunt capacitor banks at Ingledow Substation. That's going to replace the current functionality of the Burrard Synchronous Condenser Station and allow us to stop operating it in 2025, basically as soon as that's practical. It also includes installing 1 shunt capacitor bank at Clayburn Substation and 1 at McClellan Substation to meet the Fraser Valley need, as in all the other alternatives. The Ingledow option is very similar to the Meridian option, the difference being that we would install the shunt reactors at Ingledow Substation instead of at Meridian. Due to the configuration of that station, we would have to install a 500 kV shunt capacitor bank instead of 2 230 kV shunt capacitor banks at Ingledow. Both the hybrid and substation alternatives include stopping operation of the Burrard Synchronous Condenser Station. For the hybrid alternative, it happens 10 years later than for the substation alternative. And I'm going to be explaining what work that stop-off operation includes in the next slide. So before we move on, are there any questions on what's included in these different alternatives? All right.
Yes, sorry, Ms. Nielsen, maybe you can explain to me how you arrived at a partial refurbishment that would extend the life of Burrard by 10 years, as opposed to 15?
As opposed to 15 or 20, it's a good question. 10 years seemed to be a nice package of work we could do, and we were looking to assess whether there was an in-between alternative between doing a full refurbishment that's going to give us a 40-year life and the substation alternative. Like, could we defer that expenditure a little bit and get a little bit more life out of Burrard? And what we saw was that the type of refurbishment we would need to do kind of landed around that 10-year period. It's not an exact science by any means.
All right, thank you.
Any other questions? All right. So that takes us to how decommissioning and remediation of the Burrard site fits in. For the purpose of comparing the project alternatives, we decided to take a step back and also consider the cost of decommissioning and remediating the operating area of the site, assuming that that essentially would be the ultimate consequence of stopping operation of the Burrard synchronous condenser station. So for that reason, we added it to the hybrid and the substation alternatives. And in the next slide, I'll be explaining what we mean by operating and non-operating area and why we're not considering the non-operating area. So stay tuned for that piece. Because we don't stop operating the Burrard synchronous condenser station in the Burrard alternative, or at least not for a very long time, we've not considered decommissioning and remediation part of the Burrard alternative. So before we leave this slide, I just wanted to remind everyone that the preferred alternative we have arrived at is the substation alternative Meridian option. And we are now on slide number 30. Sorry, slide number 29. So let's talk about what work we've included in what we call stop-off operations, the part that is included in the project scope for the hybrid and substation alternatives. So we have to recognize that when we stop operating the Burrard synchronous condenser station, it's not just turning off the equipment. We're also going to move from that site being a site that is currently staffed 24/7 to it being an unstaffed site. So with that in mind, we've identified a number of activities that we believe are needed to make the site safe and to mitigate any immediate environmental risks for a minimum of 2 years. So why 2 years? Well, we think it could take up to 2 years after we stop operation to determine what the future use of the site would be. And we also want to leave the site in a state that doesn't require additional work in the very short term. So we arrived at 2 years. The key activities we've included are removing hazardous chemicals from site. The transformers at the site contain 700,000 liters of oil with PCBs, polychlorinated biphenyls. We plan to drain and treat that oil, and we also plan to remove the battery banks from the site. We're going to need to install a few more fire detection units in areas that are currently served by pull alarms. Obviously, pull alarms are not very well suited to an unstaffed site. And we're going to need to update our fire safety plans to reflect that the site is no longer staffed. We also plan to disconnect the gas supply from Fortis BC, as well as the main power supply to the turbine building. And to ensure cybersecurity, we would disconnect and remove computers and programmable devices. In addition to that, we've budgeted for a stage 1 preliminary site investigation that would be required to support submitting a site disclosure statement under the contaminated sites regulation. And I'm going to be talking a bit more about that later in the presentation. Before I move on to talking about decommissioning and remediation, are there any questions on stop of operations and what's included in that?
Hello, Ms. Nielsen. Chris Oakley from RCIA. Has Hydro considered a kind of, let me call it a partial decommissioning, or and I might even get into a little bit more, a run-to-fail concept? In other words, if these units still have value to the system, and I think they do, I mean, synchronous condensers do provide things that shunts aren't going to provide, what's the impact of running them to fail? Just letting them extend their lives out, because as long as they're useful, we don't have to remediate this site, and frankly, there's going to be a massive bill associated with it, so the further we push that off into the future, the longer that cost gets deferred, and there's some time value of money here, so. That's probably a couple of questions, but if we could talk about, have you thought about, running, say, a couple of the units indefinitely, or just running them to fail, minimizing the investment in the units that are in bad shape?
So a lot of different considerations obviously have gone into this decision, and one thing to consider, and I think that's going to become apparent when I show the cost of the different alternatives and how the cost builds, is that it is a very expensive facility to operate on its own. So that is definitely part of the consideration for not continuing to run it.
I'm going to take that as a code word for partially answering my earlier question. So there's no way to change the staffing level if you ran it at partial unit contingent sort of thing.
I don't know if there is I don't think I have the answer to that question right away. We'd have to go back and talk to our operations group to give you a precise
Fine.
answer
I mean,
to
if
that.
it's not a technical issue, then I imagine what it might be. So I'm just trying to see if there's a reason you couldn't just run these units out, because I do appreciate the value that they bring to the system. Notwithstanding they're 60 years old, we have lots of rotating equipment that's way older than 60 years old, and you just can milk it along as it doesn't become catastrophic to replace it. So.
Lawrence E. speaking. So on just lightly touching on the staffing level, whether we're running 4, 3, or 2 units, the impact to staffing levels is generally immaterial, given the size of the facility of what Burrard is. But in terms of the impact, it comes back down to that level of service. If we are okay waiting for the units to fail, that's something from a planning criteria we deemed as not acceptable, and that's why we're putting the effort to potentially replace that capacity today rather than be reactive as much as possible.
Okay, I think that partially answers my question, but we'll clarify further with our IRs, I guess. Thank you.
I have a question just regarding the PCBs. So this has been identified as a remediation item. Does it also become a project need consideration given federal PCB regulations to phase out PCBs and that we've seen in other projects, other CPCNs and expenditure applications? Thank you.
So the federal regulation you're referring to is for PCB levels above 50 ppm. In this case, any PCB content above that level is being dealt with separately. So when I'm talking about the 700,000 liters of oil with PCBs, it is less than 50, so it's not part of the regulatory requirement.
Thank you.
All right. I will move on to slide 30. So in the following slides, I'm going to be providing more detail on the decommissioning and remediation of the Burrard site. The part that's not included in the project scope, but is considered in the evaluation of the project alternatives. First, I'm going to provide an overview of the Burrard site and its components. Second, I'm going to introduce the concept of operating and non-operating areas. Third, I'll show the different property parcels associated with the site. And fourth, I'll provide more information on contaminated sites remediation considerations and the regulatory requirements as we understand them today based on an initial high-level review. And lastly, I'm going to explain what assumptions we've made for estimating the cost of decommissioning and remediation of the Burrard site, specifically for the purpose of comparing the project alternatives. So here is an aerial overview of the Burrard site. As you're likely aware, what is the Burrard Synchronous Condenser Station today started out as a 6-unit gas generating station. Each smokestack, if you will, you see in that picture, represents 1 unit. In 2016, 4 of those 6 units were converted into synchronous condensers, and 3 of those are currently in operation, as Ming told you earlier. Above the synchronous condenser station is a switchyard. That's what you see in the red circle there. And regardless of what happens to the synchronous condenser station, this switchyard is going to have to continue to operate. There we go. This area marked in green is what we're considering when we talk about decommissioning and remediation of the Burrard site. Since we don't yet know what the future use of the site will be, we've assumed that the end point of decommissioning and remediation of that area is all equipment removed, all structures removed to below grade, and soil and groundwater remediated to meet the contaminated site regulations industrial land use standards. Again, this is an assumption we've made for the purpose of comparing the project alternatives. It's not intended to define the scope of a future project to decommission and remediate the site. Oops, that was one too far, excuse me. I also want to mention that inside the turbine building, where the red star is, we have a control room. That control room currently supports both the synchronous condensers and the switchyard. So if we decommission the building, we're going to need to move the protection and control equipment supporting the switchyard into a new control building in the switchyard. So moving to slide 32. When we estimated the decommissioning and remediation work for the purpose of comparing the project alternatives, we broke down the site into different components. And the first one is the turbine building and administrative building. We still call it the turbine building, although it really is a leftover from its past use for generation. This is a large building and probably the most complicated to decommission. The photos you see here, especially the bottom 3 ones from inside the building, gives us a sense of the size of the facility and the amount of large, heavy equipment inside of it. The area is currently in operation, and therefore it's part of what we consider the operating area of the Burrard site. Decommissioning of this would include removing all the equipment from the building and removing all the structures to below grade, so that's not a small job. And moving to slide 33, the next area is the gas control station. And here's a closer look at that. This is where the gas supply from FortisBC enters the site and gets distributed. The area is currently in operation and therefore also part of what we consider the operating area of the Burrard site. Decommissioning of this area would include removing all the equipment and piping and all structures to below grade. Moving to slide number 34. The area shown here is the former ammonia plant. And here is a closer look at that. This was used for making ammonia that was used to assist with emission control for the gas boilers. This has not been in operation since the generating plant was converted to a synchronous condenser station and the gas boilers stopped operating. Therefore, we consider it part of the non-operating area of the Burrard site. Decommissioning of this area would include removing all structures to below grade. And moving to slide number 35. The area shown here is the former water treatment plant. And again, we have a closer look at that here. It was used for treating fresh water that was being introduced into the boilers to produce the steam for the turbines. This has also not been in operation since the generating plants was converted to a synchronous condenser station and the turbines stopped operating. Therefore, we also consider this to be part of the non-operating area of the Burrard site. To decommission this, we would be removing all structures to below grade. Moving to slide number 36, the last area I want to show is what we call the foreshore area. And here are some photos of that area. The area includes some duck banks that run along the shore. It includes some storage buildings and also a saltwater intake structure which was used for cooling water when the facility was run as a generating plant. These facilities are also no longer in operation, so we consider the area part of the non-operating area of the Burrard site. Decommissioning of this would include removing all equipment and removing all on and offshore structures to below grade. Moving to slide number 37. In the previous slides, I noted which areas of the site we consider to be in operation and which ones we consider to not be in operation. By operating areas, we mean the areas of the site that are used for the synchronous condenser operation today, the ones that are shown in purple. And by the non-operating areas, we mean the areas of the site that are no longer in operation. Essentially, that means that we could start the decommissioning activities at any point in time. In other words, decommissioning of these areas is not dependent on us stopping operation of the synchronous condenser station. Moving to slide number 38. This slide shows the different land parcels associated with the Burrard site. The red lines show the boundaries of the BC Hydro fee simple parcels. As you can see, there's one big parcel that includes the switchyard and the turbine building, and there's also a smaller parcel that includes the former ammonia plant and the gas control station. The green lines show the boundaries of the land leased from the Vancouver Fraser Port Authority. And in the next slide, I'm going to be talking about how that affects potential requirements for remediation. So moving to slide 39. I've talked about decommissioning of the different areas of the Burrard site, and now I'm going to get into site remediation. We do expect that there will be contaminated soil at the Burrard site, but we don't know the extent of that contamination yet. We have reviewed available information, and based on historic and current use, we've identified different areas of known and potential environmental concern. For each of those areas, the cost required for additional site investigation work has been estimated. We've also estimated the cost of soil and groundwater remediation to industrial land standards. Because we have limited information, this was estimated for 3 different scenarios: a best, an intermediate, and a worst-case scenario. When it comes to requirements for soil remediation, we've done an initial high-level review based on the contaminated sites regulation. Our current understanding is that investigation and remediation requirements of the regulation would be triggered when all operation on a parcel of land stops. So let me just move back to the previous slide here. So on the small parcel, the last thing in operation is the gas control station. And if we stop operating the synchronous condenser station, we will most likely also stop operating the gas control station and thereby trigger the regulation. On the large parcel, we plan to continue operation of that switchyard indefinitely, and therefore we don't expect the regulation to be triggered for that parcel. Triggering the regulation would require us to submit a site disclosure statement to the Ministry of Environment within 18 months of stopping operation. That's typically a desktop exercise based on available information. Within 30 months of stopping operation, we would need to provide an assessment of whether the site is considered a high-risk site or a low-risk site to the Ministry of Environment. And to determine this, we would obviously need to do additional site investigations. We would only be required to remediate if the site is assessed to be high risk, and we understand that to be relatively rare. For the leased lands, it's a slightly different situation. For the leased lands, we have requirements under our lease agreement to complete remediation prior to terminating the lease. And moving to slide number 40.
I'm sorry, Ms. Nielsen.
Yeah.
Commissioner Fung speaking here. When do these lease agreements expire?
So BC Hydro has just renewed the lease agreement. There's two separate lease agreements with the Port Authority. We've just renewed them for another 5 years, I believe, starting last year. And there is provision in the lease agreement to extend it as well for another 5 years without renegotiating the terms.
All right, thank you.
So the decommissioning and remediation work I've described in the past slides represent the most we would do, or what I like to call the high-cost scenario. There really is a wide scale of possibilities for the extent of decommissioning and remediation we would actually undertake. On one end of that scale is the full decommissioning and remediation as I've described and what we call the high-cost scenario. On the other end of that scale is a scenario where a potential future user would agree to take over the site in as-is condition. And in that scenario, we would need to do very minimal work, if any. And then there's a whole lot of in-between scenarios that could include a future user wanting to retain some of the assets. Maybe the gas supply would be of use, maybe the saltwater cooling system or the buildings themselves could be of use to a future user of the site. But for the purpose of comparing the project alternatives, we have assumed the high-cost scenario. So in summary, that includes removing all equipment and all structures to below grade. It also includes soil and groundwater remediation to meet the contaminated sites regulations, industrial land use standards. And as mentioned in the previous slide, we estimated best, intermediate, and worst case scenarios for soil remediation. And here we've picked the worst case scenario, again, to be in line with that high cost scenario. Another assumption we've made is that the work would happen as soon as practical after we stop operation of the synchronous condenser station, which results in a higher present value cost, again, in alignment with the high cost scenario. The other assumption we've made is that decommissioning and remediation of the non-operating areas is common to all of the alternatives, including the Burrard alternative. Essentially, that can be done at any time. It's not triggered by stopping operation of the synchronous condenser station. And for that reason, we've excluded decommissioning and remediation of the non-operating areas from the cost comparison of the project alternatives. Are there any questions on that before I move forward?
Thank you. This is Commissioner Denier speaking. I'm just, if you could share with us why at the time that the Burrard station was changed to become a condenser station, why wasn't all the equipment decommissioned at the time and the remediation done at the time? Thank you.
So some work was done to make it safe and to ensure that we didn't have any immediate environmental hazards. It's high cost to undertake any of that decommissioning, and without having good knowledge about what the future use of the site is going to be, BC Hydro has decided to defer that investment. Lawrence, do you have anything to add?
It's Lawrence Yu again here. Yeah, absolutely. At that time, it was make safe, avoiding any potential environmental safety issues for the generating portion of the facility, and then that decommissioning and future use would be determined at a later date. Okay.
Thanks, Lawrence. All right.
Sorry, I have a question as well about the Burrard site. You noted that a decision has not been made if this project's approved and Burrard is decommissioned on how the land would be used. Are there any scenarios where any of those legacy infrastructure may be of use, depending on the decision in the future on how to use the land? For example, future industrial facilities or that kind of thing that may benefit from some of the infrastructure that is there right now that the proposal is to decommission. And I raise that simply because of the fact that the substation will remain, and that site could be highly sought after for industrial uses. Thank you.
Absolutely, and as I think I did mention, it is possible that a future user, especially if it is an industrial use, could have use of, say, the gas facilities there, perhaps the cooling water system. I'm not sure about the buildings. They are pretty specific, but yes, it is possible that some of the infrastructure that's available on the site today could be of use to a potential future industrial user. All right, so on slide 41, I want to show the present value cost for each of the alternatives and how they compare, broken down into the categories that are shown in the table in the top right-hand corner. And that's the Burrard refurbishment and operating cost, the Claiborne and McClellan capacitor banks, the cost of Meridian and Ingledow reactors and capacitor banks, the Burrard decommissioning and remediation, excluding the non-operating areas as noted before, and the Burrard control room relocation. If you recall one of the earlier slides, we noted that if we're going to be removing the turbine building, we're also going to have to relocate the protection and control into a new control room in the switchyard. You may notice that there is no category for operation of the shunt reactors and shunt capacitor banks in the substations. It's not because we forgot, but because the cost is insignificant, and as Ming noted earlier in his presentation. These are the main cost categories. In this comparison, I've excluded a few very minor costs, including property tax impacts to simplify. The details of this are available in the alternatives assessment financial model provided as Appendix F for the application. So before showing the cost of each alternative, let's just remind ourselves what each of them includes. They're shown here on the screen. The operating area decommissioning and remediation cost is only included for the alternatives that stop operation of the Burrard synchronous condenser station. Decommissioning and remediation cost for the non-operating area is considered the same for all the alternatives and therefore not included. So starting with the Burrard alternative, here we see the cost of refurbishing the synchronous condenser station for continued operation. And we also see a significant cost of operating the facility for those 40 years. On top of that comes the cost of installing the shunt capacitor banks at Clayburn and McClellan substation to meet the Fraser Valley needs. And as I mentioned before, for this alternative, we've not considered the cost of Burrard decommissioning and remediation simply because it's so far out in the future. So let's move to the hybrid alternative. Here we see a smaller cost of a partial refurbishment to keep the facility operating for another 10 years versus the 40 in the Burrard alternative. And we see a corresponding smaller cost of operating the facility for 10 years. We also see the same cost as in the Burrard alternative of installing shunt capacitor banks at Clayburn and Meridian substation to meet the Fraser Valley need. In addition, we see the added cost of installing reactors at Meridian and shunt capacitor banks at Ingledow after the 10 years, which would replace the functionality of the synchronous condensers at Burrard. And lastly, we see the cost of decommissioning and remediation of the operating area of the Burrard site. We also see the cost of relocating the control room from the turbine building to the switchyard. Now let's have a look at how the cost for the substation alternative Meridian option builds. First, we have the cost of adding shunt capacitor banks at Clayburn and McClellan substations to support the Fraser Valley. Then we have the cost of adding reactors at Meridian substation and shunt capacitor banks at Ingledow substation. You're going to notice that the cost of these is a little bit higher than in the hybrid alternative, and that's because the expense is 10 years earlier, which increases the present value. Lastly, we add the cost of decommissioning and remediation along with the control room relocation. Again, a little higher because the expense is 10 years earlier. Lastly, I've included the cost of the substation alternative, the Ingledow option. Other than a slightly higher cost for the shunt capacitors and shunt capacitor banks at Ingledow, the costs are identical to the Meridian option. So what this shows us is that even when we're using the high-cost scenario for decommissioning and remediation of the operating area of the Burrard site, the substation alternative is still significantly less costly than the Burrard alternative. And as I noted previously, the scope of that decommissioning and remediation of the operating area of the site could be smaller, depending on the future use of the site, which would make that cost difference even more significant. Are there any questions on this?
Yes, Ms. Nielsen. Commissioner Fang speaking. I assume for the hybrid costing estimate, your operating costs are based on having the same 25 employees in place at Burrard only for 1/4 of the time. That's estimated under the Burrard scenario?
That's correct.
Okay, thank you.
And a similar question from Commissioner Pape Salmon, the F and the E items, as you compare option 2 with 3 and 4, is that exclusively due to the time value of money? In other words, the delay of 10 years in order to implement option B, decommissioning?
Yes, that's correct.
Thank you.
Any other questions? So that concludes the information I wanted to provide for context before getting into addressing the individual subtopics the Commission had asked us to review today. That is where I intended to break for lunch. Let's just We are 15 minutes early, so if you'd like me to continue, I can do that.
I think we should, because I'm sure people would appreciate leaving earlier.
All right.
And,
Sorry, Mr. Carpenter?
Madam Chair, just so that it's clear, after this series of answers, the last topic, we anticipate to be very short. Mr. Guite, not that he can't talk on all sorts of things other than slide 4, but isn't here to do that. We don't have much to say on topic 4, so if we carry on, we may well be done before the lunch hour.
Thank you, Mr. Carpenter. That's helpful. I think in light of what you've just said, I think we should take the break now and then maybe come back at 1:45. Okay? Okay. Thank you, everyone. Enjoy your lunch. All right. I hope everyone had a good lunch. I think we're ready to reconvene again. So Ms. Nielsen, over to you, please.
Thank you very much, and welcome back, everyone. So this part of my presentation is answering the individual subtopics that the Commission presented. And I'm going to start with topic 3A. So for topic 3A, we were asked to explain whether the Burrard remediation work is necessary to comply with legislative, regulatory, or operational requirement. For example, could we abandon or leave the site as is and not complete remediation? So as I mentioned in the earlier part of the presentation, BC's contaminated sites regulation may trigger for the small parcel where we're currently operating the gas control station, but we're going to need to do more site investigation work to determine if it would also end up being considered a high-risk site and for that reason require remediation. I also noted that BC Hydro's lease agreements with the Vancouver Fraser Port Authority requires us to remediate the leased lands prior to us terminating the lease. We don't believe that there are any specific operational requirements to remediate the site, and when we talk about operational requirements, we understand that to mean anything that would impact the operation of our assets, and in that regard, there are no operational requirements. So moving to slide 46 and topic 3B. For topic 3B, we're asked to confirm with respect to the other alternatives that remediation work at the Burrard site is not required. So again, going back to what I discussed before lunch, we expect that decommissioning and remediation of the operating area of the site is going to be required for the substation and the hybrid alternative. Decommissioning and remediation of the operating area of the site is obviously not possible as long as we are operating the synchronous condenser station, and we intend to continue operating that in the Burrard alternative. So no remediation of the operating area is required for that alternative. And as I explained earlier, decommissioning and remediation of the non-operating area is not dependent on us stopping operation of the synchronous condenser station and is essentially common to all of the alternatives. So slide 47, for topic 3C, we're asked to further explain the scope and cost associated with decommissioning and remediation of the Burrard site and how those costs were determined. We're also asked to explain the cost uncertainty or cost range associated with the decommissioning and remediation of the associated with the decommissioning and remediation estimate. For the first part, in regard to explaining the scope and cost associated with the work, I believe we covered that in the previous part of the presentation. In regard to the cost uncertainty, I want to clarify that the cost estimate range for the decommissioning and remediation estimate is +100 -35, or a class 5 cost estimate. And I want to note that there is actually an error in the slide here. It should say -35, not -50. So +100 and -35 is the same level of accuracy as the other estimates that were used in the evaluation of the alternatives.
And we'll file an updated slide correcting that, just so that it's proper on the record.
Thanks, Sandy. So because we don't yet have clarity on what the scope of decommissioning and remediation is going to be, we chose to use the high cost scenario representing the most we would do. And even though that technically favors the Burrard alternative by increasing the cost of the competing alternatives, it's clear that the cost of the substation alternative is significantly lower. Moving to slide 48. For topic 3D, we're asked to explain why we consider remediation of the Burrard site to be a separate project, notwithstanding that we are including those costs when comparing the project alternatives. So as I think we've mentioned quite a few times now, we do not know what the future use of that site is yet. And as that means that there is a wide scale of possibilities when it comes to the extent and decommissioning of remediation that's going to be required. And we can't really define a project before we know the timing and extent of that work. And waiting until we know that would delay this project and delay addressing the transmission system needs that are driving it. Slide 49. For topic 3E, we're asked to explain why we've concluded that a Class 5 cost estimate is appropriate for evaluating the project alternatives, considering the uncertainties associated with the remediation work at the Burrard site. And as I mentioned before, there's no difference in the cost estimate accuracy for the decommissioning and remediation. There's no difference between that and the other estimates we used for the comparison. As I'm sure the Commission is aware, BC Hydro's project lifecycle process supports us identifying a leading alternative based on Class 5 cost estimates and other criteria. So we essentially consider multiple criteria when we select a leading alternative, and we only prepare a Class 4 estimate when it's required to determine a leading alternative. One example could be if there was an instance where the alternatives are close on all aspects, and a more accurate cost estimate could end up being the deciding factor. If we were to, for example, look at the two options in the substation alternative, we're seeing that the costs are very close. In this instance, we have other deciding factors that are leading us to choose the Meridian alternative over the Ingledow option. But if everything else was equal and it was just that little bit of a cost difference, we would probably have needed a Class 4 cost estimate to identify which one of those options would be preferred. And as you saw when I showed the present value cost comparisons between the alternatives, the cost differences are quite significant for this project. And it's highly unlikely that a Class 4 estimate would lead to a different leading alternative. And moving on to topic 3F and slide 50. Here we're asked to provide the proposed schedule for the separate project to decommission and remediate the Burrard site. And as I think we've made clear by now, we don't have enough information yet to provide a schedule for that work. Are there any questions on these responses?
I was wondering if you could go back, it's Commissioner Pape Salmon, back to slide 43, please.
Slide 43?
With the cost estimates, and I possibly could have asked this question before lunch.
Here?
Yeah, thank you. And I'm just wondering whether BC Hydro has done an assessment of the value of the land for, potentially for sale or for other uses, industrial uses, if the Burrard condensing stations are moved. Have you conducted an estimate, or do you have an estimate of the potential value?
I know that an estimate was prepared. I don't recall what the value of the land was. It was estimated based on industrial use, and it was a very high-level estimate.
Great, thank you. And if there were such an estimate, would it be reasonable to consider it as a, if you will, a source of revenue to defer some of the cost associated with decommissioning? If it were, if it could be applied directly. So if we were to look at this chart,
right,
that there would be a negative cost box underneath, yes, that could further lower the some of the alternatives, not all of them, obviously, and their net cost to the ratepayer, for example, or to rate base. Thank you.
I think that would be a reasonable thing to do, but I do want to highlight that, in my understanding, BC Hydro doesn't have an intent to sell off the land, but potentially to make it available for a long-term lease.
Great, thank you. And then on a similar line, box B, which is operating cost, is it reasonable that the baseline case of that operating cost could be applied as a credit to some of the options that do not have that current operating cost that has come up in the discussion today? So we see with option A and B, there's an operating cost to maintain Burrard. And I understand from the discussion today that there is a baseline operating cost that if it's not necessarily tied to A and B, would it be reasonable to apply a credit for that operating cost in the substation alternatives?
So I'm not sure I fully understand which operating cost you're referring to. Is it the operating cost of the synchronous condensers and of the shunt capacitor banks and shunt reactors as an alternative to operating synchronous condensers?
Yeah, it's the current, there was a discussion about the FTEs that are currently
right.
Applied at that location.
Right.
So would there be a benefit?
So that is considered in B. So B is the operating cost of the facility, including the labor required to operate it.
Right, I see. So it's just continued, that operating cost
Yes.
is continued
Yeah.
as opposed to credited. I understand. Thank you.
Sorry, Mr. Nielsen, I just want to follow up on Commissioner Hapesam's question with respect to your answer that right now the plan is not for BC Hydro to sell the land, but you could possibly consider leasing it.
Correct.
So to the extent that you're going to be getting leasing revenues, would that not serve as an offset against some of the costs associated with the various options, or particularly the substation options that we're talking about?
Yes, it would. We haven't considered it in here because we don't know what that future use of the site is, but if we were to consider that as an offset towards the decommissioning and remediation cost, the cost gap between the alternatives would be even larger.
Thank you.
Hi, it's David Groves with the BCUC, GROHS. Just my question relates to the Stage 1 preliminary site investigation.
Yep.
So on page 29 of 57 on your slides,
Yep.
you say that this work would be required to make the site safe and mitigate immediate environmental risks for a 2-year period after stopping operations. Can you just explain what's involved in a Stage 1 preliminary site investigation? That's the first. And then the second is, could that investigation be conducted at this time?
So, what's included in a Stage 1 preliminary site assessment, my understanding is that it is a desktop assessment where we would look at all the available information we have on the site. There has been some investigative work done in the past, and we obviously have an understanding of what the historic use of the different areas of the site have been and what potential contaminants could be in the soil as a result of that. So the Stage 1 is just compiling all that information, and I believe it also would include a recommendation for what additional physical site investigations would be required.
Okay.
And to your second part of the question, could it be done now? Yes.
Okay. Has a site investigation been done on the non-operating area?
I believe site investigations have been done for some of the areas in the non-operating part of the facility, but not all.
Okay. And would that include delineation of some of the contaminated soils?
I don't know if it goes as far as delineation. I believe in the appendix to the application that explains that includes the cost estimate for soil or for site decommissioning and remediation. There is a summary of what has been done to date in one of the appendices to that. I can look up which one exactly that is.
Great, thank you.
Good afternoon. Amanda Courtney, BCUC staff, and Courtney is spelled Courtney. So I just have a question in relation to the CASA decommissioned Burrard synchronous condenser assets for the substation and hybrid alternatives. So from the public version of Appendix G-2, I note the exclusions on PDF page 136. And these exclusions include the net book value of the decommissioned equipment. And my question is, can you please explain why the book value of the decommissioned equipment has been excluded from the cost estimate for the hybrid and substation alternatives? Thank you.
Can you give me a moment?
Yep.
Sorry about that.
No problem.
So, in general, there is very little book value left on the assets. I think we might have had a few minor replacements of equipment that would have a small book value left, and we can go back and assess whether we can make that available in the public record.
Okay, thank you. And my next question relates to the Burrard replacement alternative. So you mentioned the refurbishment alternative in the presentation, but in relation to the replacement alternative, my question is, could you further explain why BC Hydro did not explore the Burrard synchronous condenser substation replacement alternative in the economic assessment of the alternatives?
Yes, I can. So, when we initially looked at the Burrard alternative, we did look at different options there as well, and we had an option to fully replace the equipment there, and we had an option to refurbish the equipment. And we did estimate the cost of both at a pre-conceptual level. And when we look at the present value cost of the two options, at a pre-conceptual level, it was clear that the refurbishment option is the least costly option from a present value perspective. And to minimize the additional work we were going to do, we chose to take the lower cost of the two options and take that estimate to a higher level of detail, the Class 5 estimate, and use that in the comparison versus going through the effort of preparing a Class 5 estimate for both options.
Okay, and if possible, can you provide the estimated present value of the total cost for the replacement option under the Burrard alternative, so pre-conception, perhaps?
I don't recall the number offhand, but we can go back and find that number. So I don't know if we should ask to have that question asked through an IR, Sandy?
Yeah, perfect. Thank you.
Ms. Nielsen, it's Commissioner Fang speaking. I have a follow-up question to Ms. Courtney's question. With respect to the replacement option that you talked about, can you tell me whether in your analysis that replacement option you consider like-for-like replacement or something less than that based on the current operations at Burrard?
So we considered, I might need your help on this one, Lawrence. We considered like for like. There were two different pieces we considered. Right now we have a hydrogen cooling system. We also considered an option where we replaced the hydrogen cooling system with a safer cooling system, but otherwise like for like.
Okay, thank you.
Chris Oakley with RCIA. Just to get back to my theme of how long can we milk this thing out, I noticed one of the important project costs is the new control building for the switchyard. And it's a pretty significant share of the costs, actually. Is there any reason for replacing the control building that's within the existing powerhouse, except that you're going to lose or take away the powerhouse or destroy the powerhouse, however you're going to actually dispose of it?
So for the purpose of comparing the project alternatives, we're just considering the full cost of building a new control building and putting protection and control in there. It's actually new protection and control equipment that would be going into that new control building. We did not consider that protection and control equipment is end of life or close to end of life already. We just took the full cost of that equipment, but big parts of that equipment would have to be replaced regardless.
Because it is getting close to end of life.
Correct.
Yeah, and of course, controlled equipment is pretty short life asset anyway, but still, you're going to have a pretty expensive building. I'm not sure what the cost of actually building the building is. We've seen on the piece Kelly that the buildings are quite expensive, just in and of themselves. So there's no, in your mind, there's no benefit to continuing to maintain the structure to avoid having to build a new control building.
So we looked at the endpoints or the extremes when we compared the costs of the alternative, which includes relocating the control room. That at the end of the day, we could, if we had to, probably continue to maintain the existing building. It is, however, a large building, and there are problems. We have a leaking roof. We've got asbestos, and it takes power to control the climate in the building, etc. We haven't done a detailed assessment of what the cost of maintaining the building for the sole purpose of retaining the protection and control equipment in that building.
So obviously you haven't looked at cordoning off that part of the building and kind of maintaining it, sort of the way they used to do with big East Coast homes, where they would actually live in a small piece of the home, leave the rest of it to kind of be cool, and just maintain that. Now, I understand that's not probably the first choice. Everyone likes a new building, and it's kind of easier to work in them. But again, just to defer costs, there's a big cost element here, which potentially could be deferred if it was possible to do that. And I guess you haven't really actually done that kind of analysis. It wasn't seen as a useful thing to do.
We haven't done a detailed analysis of what that cost would be. On the other hand, we also haven't made any final determinations of whether we relocate that control room. We initiated the project to understand what that would look like.
Okay, thank you. I probably could have found this if I dug around enough in the filing, but could you tell me what the cost of the initial conversion to synchronous condensers of the 4 units was, and what year that was made in?
I don't have that number. Lauren. Thank you, Lawrence.
The decision to go synchronous condense only was made in 2013, and then there were exercises to essentially dismantle or make safe the portions of generation that aren't required for synchronous condense. Conversion to the units have always been able to operate in sync condense mode, so it was an exercise of removing the generation portion of the units.
Thank you, Lawrence.
And I'm wondering if a person was to actually go and look, was there an application made, and could a person actually see what the scope of all that was? Okay. You don't have the reference filing. I guess I can look it up on the BCUC site. It was done that way.
Yes.
Okay. And the other question was, is there any idea, or was it stated in that original application, what the condition of the 2 remaining units that haven't been put into sync condense mode, or that aren't operated in sync condense mode? Just wondering what the condition of the 2 units that weren't converted to synchronous condense mode were at the time, and if there's any update of what they are now. Again, just considering, is it possible to do a reconfiguration and keep this thing in operation?
So the condition of those units were, I think, I'm going to say reasonable, but because we stopped generation at that facility, the units, the last 2 units actually haven't been maintained since then.
Thank you, that's my questions.
Thank you. So moving on to topic 4, I'm going to hand it over to Mike Guite.
Thank you, Katrina. So Mike Guite, I'm here to talk about topic 4, and this is the question asking the relevance in the context of additional load forecasts that have come about as part of BC's Clean BC roadmap, as well as BC Hydro's electrification plan, and how the project supports those additional loads. And I just have one slide to go through before we can take questions. So in studying the need to replace the Burrard synchronous condenser units and their supply of reactive power, we did look at several different load scenarios in our studies. And in those studies, on the bulk system, the base case we used was the 2020 reference load forecast. And we also considered several sensitivity cases, including the 2020 high load forecast, as well as the 2021 integrated resource plan electrification or accelerated electrification scenario. In that base case, the reference load forecast assumed an EV adoption, electric vehicle adoption, exceeding the targets set in the 2019 BC Zero Emission Vehicle Act target. In the high and the accelerated electrification forecasts, we assume a greater still EV adoption. In that accelerated electrification, it also it assumes a less than optimal charging shape of the load, where, say, for example, we had decreased effectiveness of the time of use rates. So everybody coming home from work and charging their vehicles at 6 p.m. rather than having charge control and waiting until we're off peak hours. The accelerated electrification load scenario also considered that by 2040, fully 1/4 of the residential heating and 2/3 of the commercial heating would be provided by heat pumps. And so we feel that in using these sensitivities load forecasts, as well as in using the 2020 reference load forecast, this project does support the Clean BC roadmap. And in summary, the project also supports the expected additional loads that come on BC Hydro's system and supports the 3 core objectives that we talked about at the beginning of our presentation today. And that included maintaining the transfer capability on the interior to lower mainland bulk system, supporting our voltage control in the metro and lower mainland regional system, as well as meeting the needs of future load growth in the Central Fraser Valley. So with this project, we are sustaining BC Hydro's system capability and meeting the transmission planning performance criteria for the near term. And with that, it's the end of our presentation. So of course we can take additional questions. Thank you. Okay, thank you.
Thank you. Niyati Goyal, BCUC staff, GOYAL. I just have a couple of questions with respect to the load forecast. So given the existing transfer capability of the interior to lower mainland transmission system is 6430 megawatt, according to the application, and the project is expecting to maintain the same power transfer, could you comment on whether there are any load scenarios where the transfer capacity for the interior to lower mainland system will need to increase over the project service life?
One moment. Thank you, Ms. Goyle. The transfer capability requirement doesn't change over the project life, and what's seen though is that the need date for meeting peak transfer comes forward in time under the higher load scenarios.
With Unit 2 out of operation, does BC Hydro have a current transfer capacity that they need to meet at this time? With all 4 units in operation, the transfer capability is 6430 megawatt. Is there a minimum transfer capacity that BC Hydro needs to meet at this time?
Thank you. Our last winter peak was 5,800 to 5,900 megawatts at peak condition, and we did meet that. So at this point in time, for present day, we're meeting our needs. The need dates for that transfer capacity were listed, I believe, on the table 2.2 of our application, which was page 221.
Thank you. Could you please explain the 4 sensitivity scenarios that you described and that were considered in the transmission planning study? Could you explain how they differ from the contingency resource plan scenarios in the 2021 IRP? So these would be the electrification scenario.
Thank you. So on that table 2.2 of the application, page 221, only what's listed on this table as sensitivity case number 4 is the equivalent of the IRP 2021 accelerated electrification scenario. And so that is that's equivalent to one of those contingency resource plans that were provided in the IRP.
Thank you. I have one final question with respect to the load growth that's expected for the Central Valley Regional System. If you could just please confirm whether the preferred alternative meets the reactive power requirements over the project service life under each of the 3 substation under the 3 load scenarios that's described in application page 2-25.
Sorry, page 2-3.
25. The substation forecast scenarios and assumptions.
Yeah. Okay, my colleague Ming Zhou is going to answer that question.
So to answer your question, let me rephrase what your question is. Is you ask, will this project alternative 3 substations meet the Central Fraser Valley long-term need? Is that your question?
Yes.
Okay. Let me be perfectly clear. Only the shunt compressor bank at McLaren substation and Claiborne substation, they are required to meet Central Fraser Valley, that local regional need. From now, I won't say now, is the project in service date 2025, 2026, until the end of 20-year period. The only 2 substations. The Ingledale substation shunt compressor bank is purely to serve ILM, but combined Ingledale, McLaren, and Claiborne substation, they support ILM. So I hope I answered your question. Only 2 substations in Central Fraser Valley, they are purposely trying to meet the Central Fraser Valley need. One will be required in 2025, 2026. Another one is 7 years apart. That 2 substation shunt compressor bank is to meet Central Fraser Valley. But this overall 3 substation shunt compressor banks, they all have to support the ILM bulk transmission. So this project is actually serving 2 purposes. One is to provide ILM bulk transmission support. One is we relocate some part of the Burrard reactive power function to the Fraser Valley region, serves the Fraser Valley, Central Fraser Valley load growth. So to answer your question, what station really serves Central Fraser Valley is the McLaren substation shunt compressor bank and the Claiborne substation shunt compressor bank. If that answers your question.
Yes. And that just to confirm that these substations, these 2 substations that support the load growth in the Central Valley region, they would the implementations, these installations will support reactive power requirements for the next 20 years that the transmission planning study has been developed for.
Correct.
Yes. Thank you.
Just a second, Mr. Carpenter. Just want to make sure I check with Mr. Bussley. Are there any questions from any of our virtual attendees?
None, Madam Chair.
Thank you, sir. All right, Mr. Carpenter.
I do this at my peril because I don't have table 2-2 open in front of me. But I'm told, Mr. Guite, you said that sensitivity number 4 is the same as the CRP in the IRP, and I don't even know whose writing this is, but should that reference have been to sensitivity number 3?
Thank you for the correction. Yes.
Thank you.
Number 3, not number 4.
Thanks. I have one final question, at least for now. And I held it till the end just because there wasn't a slide about page 3-14 of the application, the structured decision-making table that compares the 4 alternatives. And I was just wondering if you could speak generally about how you conducted that trade-off analysis in terms of weightings. And so, I point out that capital cost is featured prominently in the application, and that's the first line. We've heard about the need for voltage control and VAR, and I see, a row there that compares the preferred alternative 375 MVAR versus a Burrard refresh 525. And, other factors, I'm curious as to the relative weighting of those criteria in terms of the trade-off analysis and how you came to at a high level, the conclusion of the Meridian option, given, for example, looking in column 3, which is the Burrard alternative refurbish option, there's quite a few green boxes. So the capital cost is significantly higher, 3 times, but there are some, advantages, if you will, even though it's potentially a legacy technology, as we learned from your helpful presentation this morning. Just a general commentary, and if you prefer to answer this in IRs, that's fine. I just wanted to plant the seed for a discussion about the weighting of the criteria. Thank you.
So I can provide at least some level of answer to this, I believe. When we're looking at maximizing system operational flexibility and maximizing reliability, for example, I want to make sure that we all understand that each of the alternatives we have selected meet all the criteria we have for the system to operate. So in a certain sense, where you're seeing higher scores for the Burrard alternative, it does have some benefits, but they're not necessarily benefits that are required for us to operate the system reliably and with the flexibility we need.
Great, thank you. And just one final point of clarification. Under the synchronous condensers, they consume natural gas, and is greenhouse gas, is that right? Do they consume natural gas to operate? No, they're operating independent of that. Thank you.
Are there any other questions from anybody in this room or from our virtual audience? Okay, hearing none, I think we're in, unless BC Hydro would like to make any kind of closing statement.
I don't think we've got anything left to say, Madam Chair.
Thank you, Mr. Carpenter. Well, I think that I want to, on behalf of the BC Utilities Commission, the panel and the staff, I want to thank the BC Hydro panel for sharing your expertise and knowledge with us today. I really appreciate it. Certainly, I found it very helpful, and I appreciate you taking the time out of your day to come and help us understand a bit more about the application, particularly on a snowy day in February. So I want to let you know, I believe most of it is melted, at least I'm hoping. And I want to thank everyone for putting up with a new venue. It's a little bit strange for all of us, I have to say. But overall, I thought they went very well, and I really appreciate everybody's patience. And hope you get home safely this evening. Take care, and thanks again to everyone.
Thank you.
Thank you, Madam Chair.
Thank you.
Thanks.
Yeah, please tell your mom. Coffee's there. Thank you.
No, I You're welcome. Oh, and vice versa. I told my wife and son, I said, I think this is when son said, I think I'm starting to understand. Those were almost the exact words that I told my wife and son the other day. And I said, okay, so tell us about it. So then I started saying things, and then I started asking the questions, and I realized all I was really doing was just taking your words and passing them on.